Good morning. Welcome to this morning's session on AstroFest. This morning we have a talk by Steve Conrad. He was the lead engineer on the Lori instrument on New Horizons, the one that went out actually beyond Pluto now. Steve's talk this morning is on the IOTA's work on occult timing. Steve?
Thanks, Art. Can we get my slides going? Do I get a clicker, or should I be standing here, or what do you guys want? Sorry, I should ask beforehand. You want me just here?
The camera will follow you. So.
Okay. Hi, everybody. Has anybody seen this show, the Nova that came out earlier this year called Star Chasers of Senegal? If you get a chance, watch that, because about half of that show is about occultation timing and a NASA expedition to Africa to collect data for the Lucy mission, which, by the way, I also was involved with. Anyway. So if you were looking through, I will call a moderately sized telescope in constellation Sagittarius in my hometown now of Wellsboro, 3 days ago, October 3rd, you would have seen this. Okay, how do I start the video? Did I hit the wrong button? There we go. Okay, so you see the arrow pointing to that little star? If they go away, come back. So that is what I do with most of my telescope time at home, is look for stars to blink out, and that's called occultations. So the agenda, we'll talk about what they are, why I do talks like this to try to recruit more observers, some example typical results, unexpected discoveries that we make, pro-am campaigns, a little bit on how to do it. If you're really interested in pursuing this, I have contact information, or you could talk to me afterwards. I'm always happy to talk to people about how to do this. The organizations involved, IOTA and the Astronomical League. I'll have a list of upcoming occultations for your observatory here, and some closing remarks. So what are occultations? So it's when one object hides another object so you can't see it. In astronomy, you can further specify it as lunar, when the moon goes in front of stars or solar system objects. Planetary, when a planet does the same. And what I mainly concentrate on is asteroids, when an asteroid hides a star. So the geometry of an occultation is as shown here. So imagine the star is effectively at infinity compared to other distances. The asteroids we measure are typically 2 to 3 AU from the Earth, but sometimes we do Centaurs and Kuiper Belt objects, which are highly sought after, and they're much further distant. But you can see the basic geometry here. We have 5 observers scattered across the path. So we have a shadow path that generally goes west to east across the globe. And, we call it the shadow, even though it's not, not really losing any light that you really care about. You lose the light from that star. So here we have 5 observers. We have 1 up in Canada. We have 1 in Wellsboro, where I live, 1 in Virginia, and so on down the coast. And this is a very large asteroid, by the way, but for representative purposes. And we all watch for when it disappears and when it comes back. And we time that to very high precision. We try to time it to at least 10 milliseconds, if not 1 millisecond. And you can see what the 5 observers would see. The observer up in Canada, the star never blinked out. From my location in Wellsboro, it blinked out for a short time. The guy down in Virginia had a somewhat longer time, as did the person down in South Carolina, and then the person in Alabama got nothing. But from that, you can make a shadow diagram of that aspect of the asteroid. So we're able to get a good measurement of the size and rough shape of the asteroid, and the more people who observe, the better a measurement of the shape we get. So why do we do it? We measure the size and shape of asteroids. So to construct that silhouette like I was talking about, the critical requirement is to have multiple sites covering the potential path. These events can happen anywhere, anytime on Earth. So they can happen at the North Pole, the equator. They can happen in broad daylight, though you can't generally measure them in broad daylight. And amateurs and professionals are doing asteroid light curve measurements all the time, right? Where you're looking at an asteroid, you're looking at it get brighter and fainter and brighter and fainter. And they have very sophisticated software to enable them to measure the shape of the asteroid, but they can't measure the size without making assumptions on the albedo of the asteroid. So we fill a critical gap with size because we have absolute truth of size, and we can also help them with irregularities, things that point inward and outward. Sometimes they have trouble resolving with their software when they do a light curve analysis, and they won't know is there a bulge out or is there a bulge or a crater in. We also get very accurate, super accurate positions of the asteroid, improving the orbit knowledge, and that's mainly from the Gaia data, right, where we've got, hundredth or thousandth of arc-second measurements of the stars behind it. So when the star gets blinked out, we know the geometry, we know the location in the orbit really well. We're also able to resolve very close double stars and also measure stellar diameters very well in the cases of like large red stars, for example. And then there are rare but very important discoveries of rings and satellites. And it's also what I call a neat party trick, because my wife has no interest in astronomy, but she likes seeing the stars blink out. She just thinks that's kind of cool. So why do amateurs do this? Why isn't this a pro sport? Why is it an amateur sport? And mainly it's because you don't need big equipment for most of the stuff we do. Most of the people doing this are typically using 8-inch telescopes, somewhere around that range. The more, bigger telescope you got, the fainter stars you got, the more events you can time. So bigger is generally better, but it's not required. The other advantage amateurs have is sometimes you want to travel. There's a lot of people who would travel to important occultation events into the path. And amateurs are used to throwing all the stuff in the car and driving to Cherry Springs or wherever. We're used to going places. You ask most professional astronomers if they can move their equipment, and they're going to say, you can't move a 60-inch telescope. We're also scattered throughout the world. These don't just happen in southern Arizona or Hawaii. They happen everywhere. And it's also a very part-time activity, right? So most professional astronomers aren't going to be able to make a full-time job out of timing occultations. But even though we're amateurs, our results are published. Oh, hit the wrong thing, sorry. You got to keep things away from my elbows. I guess just back to full screen mode. There we go, okay. Thank you, sorry about that. But even though we're amateurs, our results are published, and professional astronomers and planetary scientists ask for our assistance quite regularly. NASA has paid us to go with them to collect this data in advance of flyby missions. So even though I was working on a NASA program, I took vacation time to have NASA pay me to go to Argentina twice back in 2018. Before we got to Arrokoth, to measure the size and shape of Arrokoth before New Horizons flew by it. So we need more observers, especially me living up in northern Pennsylvania where none of my old occultation buddies in Maryland live. I had a a good cadre of people down there helping. Up here, I don't have anybody, so that's why I'm giving a lot of these. So here's an example of our problem. Here's a list of observations, 31 observations made earlier this year, February this year. And you can see 27 of the 31 are single chords. So we got one line across the asteroid. When we do that, all that tells us is the asteroid has to be bigger than this in this dimension, and we know it was across the star at a certain time. So we do help the orbit, and we do get a minimum size, but we can't fit a circle or an ellipse to 2 points. It just doesn't work. So we really need more observers in order to make this more valuable science. So here's another example. This was from about a month ago, I think. Boy, that went fast. Let me try it again. But it's going to blink off for like a half a second. There. But you noticed it didn't go completely away. So this was what I did. I was unfortunately the only observer on this one. There were actually people signed up, but the other people got clouded out. But that star was supposed to completely blink out, but it only blinked about half out. The only reasonable explanation for that is it was going across a double star and only occulted one of the two double stars. But since there were no other observers, you can't do anything with that. You can't verify it. I'll show you examples of how you do that in a few minutes, but you know, I knew what I had, but there's nothing I can do with that science. Oops. There we go. So it's interesting, but the problem with not having enough people, enough observers, is actually partly due to our improvements in our ability to predict these things, which is kind of strange when you think about it. But before the Gaia data, which is so high resolution mapping of the stars, we were used to only be able to predict for larger asteroids, you know, like ones in the first 400 or 500 asteroid numbers typically. And we had large error bars in our paths. So these paths were wide because they were big asteroids, and then you put a big 1 or 2 sigma on that, and you made it 2 or 3 times wider. So now it's covering many more people. We were predicting fewer events, so people were more willing to travel to those. And as a result, we ended up having more people signed up for the typical events, and we'd have more observers. But now we can predict for these tiny asteroids, which have all sorts of cool shapes, by the way, because the smaller you get, the more irregular they are. And the one on the previous page was 12 kilometers across. So now what people do is they can stay home and they can sign up for half a dozen or a dozen events a week from their home observatory, not have to get in the car, and, you know, and I'm criticizing myself here because this is what I do. And we get a whole bunch of single chord data, so we get nice orbital information and not much else. And that's just a chronic problem now we're having. Some example results. So here's a typical one for now. This is from a Jupiter Trojan, which is highly valued, by the way. We only had 2 chords across this one. Kevin Green down in Connecticut and I happened to be roughly along the same line. So all we can do is to draw a circle in that. You can't even draw an ellipse. You need 5 points for an ellipse. We only have 4. So, okay, we got a decent measurement of what its size is, but that's all we have. We don't know how irregular it is. You know, it could have a huge blob on the other side or a big crater taken out of it, and we'd never know. And like I said, this is probably our significantly better than our average single chord observation. Now, when you get to like the Iris one on the left there, where we had, 5 chords across it, now you're starting to get some pretty good data, and you can start to see the irregularity. Look on the right side, where the cluster from 2 to 4 are purple, brown, and whatever, greenish, you start to see some of the irregularity there. And then when you throw everybody at it, so the Antiope event on the right side, this was for an IOTA conference. So they timed a conference for Antiope's occultation, and they had 50-some chords across it. And you could see the wonderful mapping we have of that double asteroid. So this is the power of what we can do with small telescopes. And this was all done, Antiope was a very bright event. It was done with a lot of 2 or 3 inch telescopes that people will deploy and leave behind on the highway. Not on the highway, just off the highway, of course. We get in Sky and Telescope every now and again. So, you know, here I am in Sky and Telescope at the middle court from my old home in Maryland with a bunch of my Maryland buddies, and just happened to go across my friends out in Arizona. So it was all Maryland and Arizona for this group. So we, you know, every once in a while you can say, hey, my name got in Sky and Telescope. So now I mentioned the light curve people. So we can take our data and put it in the light curve and expand or contract their basic shape and see how well we match. So here's one we did, I forget which one this is, but it doesn't matter. And you can see we matched their shape really well. You know, it's kind of a boxy looking thing, and that's what we found. So we were able to scale their light curve analysis to the right size. But you get ones like this. So you see the aqua or whatever color right through the middle of the asteroid, that doesn't match at all. And you can't make that match. So, you know, this is one you'd want to take, oh, we need to observe this one several more times from different aspects as it rotates around and figure out what's going on. Okay, unexpected discoveries. Here's Agamemnon, and this is one of mine that, you know, it happened 11 years ago, but it's like still a really important one. And since it was my chord that was the important one, I always need to bring it up. So anyway, back in 12, there's 5 of us set up 7 stations to measure a large Jupiter Trojan Agamemnon. So all the observing stations were in the mid-Atlantic. 5 got successful chords. We got a very good measurement of Agamemnon. It's a large rock, so it's fairly circular or elliptical, I guess. But my chord, which was very high signal to noise because it was a fairly bright star and I was using a C14, I had a second occultation 10 seconds later. The best explanation for this is it was a small satellite of Agamemnon. So here's a plot of the data. You see it going across. So signal level in DN is up at the 4,000 level, went across, dropped down to 0 because Agamemnon's much fainter than this 10th magnitude star was. So basically the light just entirely goes away for about 10 seconds, which corresponds to my chord across the Jupiter Trojan, and then came back, and 10 seconds later, it went away for 0.6 of a second. And I was watching it, and as soon as I saw it, I knew exactly what it was, because that's the only other reasonable explanation of it. Unfortunately, it was a small satellite, so none of the other guys got it. So there's only one chord. So that is not adequate proof, you know, for saying we got one. We did write a paper on this with one of the scientists out in California, you know, saying that we have evidence for a satellite, but we don't have proof. And if it had been proof, it would have only at the time been the second Jupiter Trojan to have a satellite. So here's what the plot looks like. You can see the Trojan looks nice and elliptical, and then out here is the satellite, or a potential satellite. So we think it's of order 4 kilometers, could be as small as, I think, 2 or as large as 10. And they do that by looking at the diffraction from that. We did check to see if they had done adaptive optics of Agamemnon before, and they did. But when we talked to the scientists, they said that that size satellite they wouldn't have been able to resolve. So the fact that it hadn't been detected by ground-based observations directly doesn't rule it out. We also did all the other things like, could there have been in January a bird big enough to cover a C-14 for 0.6 of a second? We talked to people from the Audubon Society. We said, okay, what about an airplane? Could an airplane possibly go slow enough to block it out? And you do the math and it just doesn't work, doesn't even come close. So the only reasonable is it's a satellite. And there's been other satellites that have been found this way, including ones with multiple chords across them that were slam dunks. And like I said, we did publish a paper on that like a year after we found it. Another type of discovery, same year, 9 of us were looking at a main belt asteroid, which I would butcher the pronunciation of, so I will leave that. Cross-country event, California to Maryland, and there were 6 successful stations. We made a good measurement of the size of that asteroid, but we found we had a double star, and here's how we found it. So there's the light curve plot there at the bottom. I'll mention 3 of our chords were very low signal noise. They were the tiny little telescopes, so you wouldn't be able to tell the step function that you see down there. You see where it drops down, stays at one level, then drops down to 0, goes across. And then on the way back up, there's another step there, but it's a little harder to see. So the 3 low signal to noise, you couldn't detect that. The 2 high signal to noise ones, mine and one of the other guys, this was the other guy, very evident. Except mine, which is the purple one right at the limb there, I only got an occultation of one of the 2 stars. And that had a lot of people scratching their head because until we realized it was a double star and we had that other data point right through the middle, we were thinking that why didn't mine go to 0 like everybody else's? So we published a paper on that in the Journal of Double Star Observations, DSO. And it turns out that this is a variable star of the FU Orionis type, and the theory for that type of double star involves variable star, involves a really close double star. So the author of the paper on that type from 1997 was very interested in our data showing it was a double star. Pro-Am campaigns. So there were ring discoveries. This is a Centaur object, Charlie Kilo, or however you pronounce that. These observations, this was actually the Wasilla 1.5 meter telescope, but there were amateurs on the same discovery who also found the rings. And you can see what rings look like. There's 2 rings on this one with these drops before and after, very symmetrical about the main body of the Centaur object. There's Pluto. So back in, was it 18? We had the really good Pluto occultation that followed that red line down through the country. So a group of us IOTA folks borrowed observatories like your observatory here. I used the one at Lynchburg University. They have a 20-inch down there. One of my cohorts used the one at Liberty University. They had a 24-inch. And we even had a science center down in Houston. They had a 36-inch at the science center, all looking at Pluto. What are you looking at Pluto for? We know the size very well and all. We're looking at the atmosphere. After New Horizons went by, they're expecting as Pluto goes out, the atmosphere may collapse. You can measure the atmosphere by the fact that it's not a sharp event. It doesn't cut off instantly. As a star goes into the atmosphere, it fades. And then the really cool thing is if you're on the center line, you get a focusing effect of the atmosphere, and you get that spike in the center that goes up. And that is so finely tuned. I was on the north side of Lynchburg. I did not see that, where my cohort on the south side of Lynchburg at Liberty University, she got the spike. And that was Roxanne Kameen, by the way. Some of you probably know her. And then there's the New Horizons results. This is when I was sent with a 40 or so IOTA people down to Argentina twice to try to get this data. So when New Horizons would go by Arrokoth, we would know how big it was. So where do we need to point our little soda straw camera? Did we need to do a mosaic at closest approach or not? That's what this data got from us. And you can see the 1, 2, 3, 4, 5 chords we got across, match almost exactly what the New Horizons found. So very powerful technique, and that has encouraged NASA to do this with other missions, like Lucy, for example. And here's a Lucy one. This was one I was involved with last year. For this one, I borrowed the Observatory, University of North Carolina, Asheville. And they have 2 telescopes there. I had 2 pairs of undergrads running the telescopes, one with an analog camera, one with a digital camera, just for redundancy. And all those undergrads took the data, they got the credit for it and all, and they were just living big. And I have a ball working with kids like that, so it was really cool. We had the middle chord, the one that goes through the asteroid, Palamedes, the middle one. But some of my cohorts who didn't get an occultation of the main body, like 15 seconds later, got an occultation by a satellite. And there's multiple ones there, so that's bulletproof. So now, when Lucy goes by this one in 2029 or whenever it is, they have to point to 2 things. And of course, once you find this, you need to figure out where its orbit is in order to point in the right direction. So when they get data like this, it means we need more data. So Lucy, Mark Bowie of the Southwest Research and his team, they've been collecting data with IOTA participation and other amateur support all over the place. They've gone to Australia several times. Roxanne got to go to Australia for those. And then we even applied it to the DART mission after they impacted the Dimorphos, I guess Didymos was one they hit, right? The little satellite asteroid. And nobody thought we'd be able to measure the little satellite asteroid, and we being the big global IOTA sense, not me. And we were able to do it, and it's these data that are really telling them, how much they slowed down that orbit, because this is absolute rock solid data. So how to observe them? So you need advanced knowledge, when they're going to happen and all. So we have software called Occult that allows you to do your own predicting. All our software is free, of course. And we also have one called Occult Watcher that allows you to just use other people's work and say, hey, I want to know what ones happen here at my observatory. And it has to happen at my observatory. It has to be higher than a 50% chance, yada, yada, yada. You put all those things in, you hit the button, and you get a list. So you need predictions. You need to get a number of observers across your path because there's, like I said, limited value if it's just you. You need to know the location of where you are, but that's trivial. You just need to know that to a fraction of a kilometer. Is more than good enough, so you could even use a map, not even a GPS for that part of it. For total occultations, where the asteroid's much fainter than the star, so it basically blinks out the star entirely, you need very low signal to noise, like signal to noise of 2 or something is good enough. So typically an 8-inch telescope at f4, you can get to bag 12 or something like that. You need the time to, ideally, 10 milliseconds. Now, as we go to smaller asteroids, we're probably going to start pushing towards 1 millisecond. Our typical cameras that I have up here, if you want to talk to me about the cameras afterwards, happy to do that, easily timed to a millisecond or better. Other things you need if you're going to use an analog camera system, the old NTSC, focal reducer, cheap stuff is fine because your field of views are tiny you care about. You just need your main star and maybe 1 or 2 reference stars around it. You need a video camera and power supply. They can be as cheap as $160. A lot of these things you probably already have. Time inserter, I have one in that box there. They're about $250. That put the time on the bottom of that video that you were seeing earlier. Video display, something like that I've got in my basement. Video recorder, which now is a dongle for your laptop. That's $35 an order. So you can see, it's not free to get into this, but it's not super expensive either. And then there's also cameras that are specifically made for this, like the QHY camera I have here. And that has timing built into it. It's all self-contained. You just plug it right in with the USB connector to your laptop. And you can use that camera for other things. Some people put it all together in a box with a battery and all, so if they travel, they can just open the box, plug in their camera to the telescope, and they're ready to collect data. And the guy who invented that called it a score box. My comment about the grocery bag, the first time that David Dunham, the guy who really perfected the sport of occultation timing, gave me a grocery bag full of equipment, this is 15 years ago, and said, "You're an engineer, you'll figure this out." Well, I had it figured out and running about an hour after the occultation happened, so that didn't work out well. Analysis and reporting, we actually have 3 different software packages now, actually 4 if you count Astro Image J, that can be used for this, to analyze your data. And then we have statistical packages that'll even say, give you the 1, 2, and 3 sigmas on your disappearance and reappearance times. So very sophisticated software, again, all free. And then we have an Excel chart you fill out, or the software fills out for you, that you send to your continents coordinator, and then they put all the data together, quality check it, and then it gets submitted to the Minor Planet Circular. And every quarter, generally, they have an article in there, and you're credited as an observer. So this is the Tangra software package that I typically use that just shows you how it does a plot and shows you where they are. And from that, you could pick out easily to 30 milliseconds where your times are without even using the statistical stuff. Here's the form you have to submit with all the where you are, when you are, what telescope you used, all that sort of stuff. And they do check up on you on this, because about once a year, I'll have the quality guy in Australia will contact me saying, "I think your latitude's off by a couple of tenths," that type of thing. If you get a video system or one of the timing systems, other things you can use it for, a lot of the meteor people who have the all-sky cameras use the precision timing on it from multiple stations to try to correlate things. There's lunar and also Venus meteor impacts now. And not kidding about this, but apparently one of the biggest markets for these cameras are the UFO people, because they all want to compare their data. Okay, so IOTA and the Astronomical League. So IOTA is a worldwide organization supporting occultation measurements. I think we're $25 a year, but honestly, you don't have to become a member. The only thing the membership gets you is you get the journal sooner if you do that. But at $25 a year, we have conferences every year. I think it's a worthwhile thing to be involved with. We use, I keep meaning to change that. We use a Groups.io group for communications. We have all the free software package. We have a 500-page manual you can download for free. That will tell you everything you need to know. And we're not just asteroid events, we're also lunar occultations where the moon just goes straight in front of a star. And if you do 100 of those, you'll probably discover 1 new double star. So if you want to discover stuff, you just wait for the moon's dark edge to be going by a whole bunch of star field, and take an hour's worth of data and then go analyze it. You might find a new double star, and you can write a DSO paper on it. We also do lunar grazes, where the bright star goes by the edge of the moon, and you watch it blink in and out for the mountains on the moon. That used to be important for measuring the height of the mountains on the moon, but now with laser radar on the orbiters they've had go to the moon, it's not useful data anymore, but it's really cool to see. It's kind of like a rock skipping, when you throw a rock across the water. That's what it reminds me of, the star blinking on and off. And there's like informal competitions of how many blink outs you can get. And there have been observations in the mid-teens for how many blinks you got on a single star. We also do stuff with solar eclipses, planetary satellite mutual events, and things of that sort. So there's a lot of varied interest in our group. Astronomically, why do I throw them into the mix? I throw them in because there's a occultation program that they have that I administer, and I've given away one so far. So there's only one person that got it. So if you want to get badge number 2 or whatever you want to call it, you can go through our program and do that. And then there's also the Citizen Science Special Program. So if you do, there's all sorts of things you can do for like variable star observing and all, but IOTA's in there, so if you do 100 observations that you report to IOTA, whether they're positive or negative, you get the bronze level, you get 500 for silver and 1,000 for gold. So if you're into collecting the AL things, that's another potential one. Upcoming events here at your observatory. I've got 3 pointed out with arrows. This is the output of Occult Watcher software. So there's one, what date is that? October 9th, Monday. That's a 67% one from here. 67 is pretty good. I basically do everything that comes over my house that's 10% or more. Then you have one October 12th, which is next Thursday, that's basically 100%. And then there's one that is 100% down on October 23rd there. So, and interestingly, these are just, random, are they good or bad? This is a bad one, the one I gave to the Mars Observatory people when I gave this talk a couple weeks out of there. They had many more, but you wait a month and there'll be more here. You get months that are good, months that aren't so good. Here's what I think your best one is, Monday the 23rd. Unfortunately, it's at 3:30 in the morning. It seems like most of these are. Astrea will occult a 12th magnitude star for as long as 11 seconds. You're basically a sure thing from here. Huge path. Astrea is a big asteroid. Basically, the path covers Ithaca to Scranton. So you guys are about in the middle of it. Only has a magnitude drop of 0.3. It's not going to make the star completely blink out, but you will notice some 0.3 drop to your eye. The software will have no trouble with it. Quite high in the sky, so it's all good other than the 3:30 in the morning part. Ooh, that didn't come through. Okay. Well, that was just the path where I told you. It's basically an east-west path covering Ithaca to Scranton. All right, closing remarks. So oftentimes I give these talks and people say, oh, IOTA, yeah, I used to do that 20 years ago, but you guys would tell me it was a 70% chance that I'd never get anything. I tried 12 of them, I never got any. Well, now that we have got the Gaia data that we've been using for the past couple of years, our predictions are really good now. So that's why we're able to do really small things, and the big ones are sure things. What I've noticed for me is I seem to have less than I used to that meet my 10% threshold, but I get more hits of the expected level I do. So I sign up for typically 10-ish events per month from my home observatory without getting in a car. But due to our weather, and your weather's probably pretty similar here, I get maybe 30% of them in wintertime with the clouds and 50% in the summertime. It's a really seasonable activity too. If you ignore the weather, you get many more in the wintertime than summer. And that's because night is a lot longer in the wintertime, and the ecliptic's higher in the sky, so if you have a cutoff of 20 degrees or whatever because of your tree lines, you just get more. So unfortunately, the good weather time you get less, and the bad weather time you get more. So just my comments on positives and negatives of this. It is amateur contribution to real science. And this is something, as I was telling you earlier, you can get into this, get the equipment, and in a couple of weeks you can be submitting your first data and get scientific credit for it. It's a team sport, and it gets you out observing more, because when I have a friend who signs up, like my buddy in Connecticut or another guy in the Adirondacks I work with a lot, when he signed up, it's 3:30 in the morning, my alarm goes off, and I'm saying, oh God, I really don't want to get out of bed. It's too cold out there. It's like, Kevin's doing, I got to do it. I can't let him down. So you have the little bit of peer pressure, which is a good thing. It gets me using my equipment more. And like I said, amazing the freeware we have, that stuff that they can do with that. So the negatives is the weather will break your heart. Because not only do you need clear skies, you need clear skies at a specific direction at a specific time. It's not like a faint fuzzy where, oh, okay, that cloud will go away, I can take the picture of it starting in 5 minutes. No, that cloud will go over you at the wrong time all the time. And then there is the cost of the hardware. To get into the NTSC, the old analog types, probably of order $500. To get the latest and greatest QHY camera is like $1,300. So it's not free to get into. And just some resources. Since IOTA is an old organization, everybody started their own website. So there are all these other IOTA websites that never have been consolidated together. So it's just something you have to deal with. The observing manual, that's the 500-page thing I was talking about. And I'm thrilled to help people get started on this because, like I said, it's my pyramid scheme and I need more people. So you're perfectly welcome to contact me, and I'm happy to get you started. Questions? Sir?
How do you actually timestamp the video that you take?
So if it's NTSC, the old analog type, like old television from 30 years ago, what we do is we put that through directly into a time inserter, which is this box here. So analog goes into it, and that has a GPS built into it, GPS antenna, and it puts on the bottom, the times you saw on the bottom, it puts that right in your video. So there's no delay time, it's all calibrated out, and the software takes care of that. So that's fairly easy. The big problem there is you got a $250 box that there's probably not much else you're going to do with it. This guy, the QHY camera, has the GPS built into the CMOS camera. So when it starts an exposure, it says, what's the GPS time? Put that in the metadata with the FITS file. Halfway through, what's the average time? What's the end time? And they're all in the file. And then our software goes through and interrogates the metadata for that.
So you don't need to be on the internet?
No, you just need to have sight line to the constellation of GPS satellites. Anybody else? Art?
You're going to demonstrate some of this equipment now. Is that right?
Well, there's two things, right? There's over on the left side, I've got occultation timing equipment. I've got the 2 cameras. I've got the timing box here right now. And back here, this annoying flashing light that we use to attract people is what we use to calibrate our cameras. You don't need this. This is for new cameras. Things like this, they've all been calibrated. They all behave the exact same way. The QHY people, multiple people have tried to find issues with QHY and never have. So it's just when we have new technology. And by the way, we have some new technology that's just coming online involving Raspberry Pi. And there's a camera kit that probably will be available in a couple of months that is going to cost about $500 and about 15 minutes of time with a screwdriver to put together. And that camera has some of the coolest features this guy up in Calgary put together to guide you to your target. So the Raspberry Pi will have loaded on, you need to go to RA this, DEC that. You put it on, you point your knob roughly in the area, it'll say move left, move left, move left, move up, move up. Okay, leave me alone now. I'm going to wait for the star to come across, and it'll drift across, take the data, turn itself back off, and then you pull the memory stick out, and you plug it in, and you got your data. And that is going to be so slick. So I'm going to be one of the early testers, so about 3 weeks from now, I should have my kit and start putting it together. But that's going to open up a lot of opportunity for people. sorry, I got off topic. I chased a squirrel here. But anyway, that equipment I'm happy to chat with people about afterwards. On the right side, I'm also, for citizen science, doing spectroscopy. So I've got a spectrometer set up here that I can do a demo with during a break or something. Happy to show you guys that. There's a lot of potential science here. And I've also talked to a couple of you about the potential science, maybe using your observatory for looking at cyanide jets from comet nuclei, which takes special filtering, and also special occultations where we need a big telescope, like there's an occultation coming up of Neptune's rings a couple of weeks from now, where you need a big telescope and you need a methane filter to work out in the IR. So I'm really about emphasizing citizen science. I mean, I have complete respect for people who do faint fuzzies and take pictures and all that stuff, but that's not my thing. You know, I like to do stuff where I feel like I'm contributing to science.
Why don't you take about 15 minutes or so showing people stuff right now. I know the speaker on the next talk, if he could get through it in less time, he's alive. So that's the next speaker.
We do have a couple things from the chat, though.
Okay.
A couple comments and questions. First, from one of our board of directors, Mike Blake, he just wanted to comment that he knew very little about this field and found it fascinating. So it was good to have this contribution to asteroid knowledge. He also follows up with a question: do they have any remote stations that can be programmed to look for the occultations?
Well, there's two different answers to that. One is we have the side of the road stations, okay, where there are people who have set up as many as 12 or 14 stations for a single event. And these are these little, what they used to do is they would go to Walmart, buy binoculars, cut the binoculars apart, and use pipe fittings to put a camera on the back of that, and then put it on a cheap camera tripod. So those they would drop by the side of the road and they'd be unattended. But the bigger question is, there's a guy now, Mike Skrutsky down at University of Virginia, who has put together a system that basically he leaves it in his backyard, and any low probability, high probability event, his telescope just says, oh, time to wake up, slews over here, takes the data, goes back to sleep. So that's what I'm also intending to do with my observatory. I'm working on automating my dome to be able to do that. So there aren't stations that are permanently just dedicated to that yet, but there may be in the future.
Right. And I actually had a question myself. Just as I try and understand this process, are you able to obtain 3D data using this method, or is it purely a silhouette?
No, you get one plane.
You get one, okay. And
but if you take multiples, you get rotations, right?
yeah, that's what I was kind of like as a follow-up. Are you able to, for something that's rapidly rotating, what do you do with an object like that? Is it possible to actually get an accurate?
Well, the good thing is none of them are rotating fast enough where it matters realistically across the path, because the path across the Earth is typically 5 minutes, maybe 10. And fast rotators are a couple of hours, something like that. Otherwise, they fly apart.
Yeah.
And some of them are, probably our typical ones are 10-hour rotations, something of that order. So that's really not an issue at this point.
It's a quick shutter speed, almost, so to speak. Yeah. When it crosses this.
Yeah.
This
Yeah, you can think of it that way.
Okay. All right. Well, I think that's. What's this one? Let's see. Oh, that's a question for me. Never mind. So I think we're all set. So thank you so much, Steve.
Yep.
Cacciola. I'm a member of the Kopernik Astronomical Society and one of the organizers for AstroFest. Welcome. This morning I'm going to give a little talk about what we're calling the Everest Mirror. So tonight, I was thinking I was doing this at night, I'm doing it in the morning. We will learn a little bit about the little piece of glass on the display to my right over there. It was made locally and it's a part of a national astronomical history. So let's go back and talk a little bit about the history here, starting with George Hale's vision. So in 1928, the famous astronomer George Hale had a vision. He wanted to build the world's largest telescope at Mount Palomar in California to do research. He wanted an instrument that would allow scientists to view the skies as we've never been able to do so in the past. So we're talking a little bit here about the Hooker 100-inch telescope at Mount Wilson. So the creation of the largest single piece of glass ever made was entrusted by Hale in 1929 to the Corning Glass Works using their signature Pyrex. Why? Well, because this special glass is designed to resist heat expansion, which, as you know, is very important in astronomy. But right at that time, the largest mirror was installed to the Hooker telescope at Mount Wilson in California, and it was 100 inches. So he's gone back to Corning and asked them to make a 200-inch. So Corning Glass Works in Corning, New York, just a little ways down the road from here. They wanted a batch of glass with the lowest expansion glass, had to be prepared for testing they called the Great Eye back in the day. So in 1933, ladles of molten glass were transferred from a tank into the mold. So this was a test. The disc, after being annealed for 5 months, was built into a special crate and loaded, and the test flat was shipped by truck and rail from Corning down to California. So now we're moving forward a little bit, and we're talking about the 200-inch. So in 1934, they tried pouring the mold for the 200-inch, but part of the mold broke loose during the pouring, and this failure caused a big crack, and it's a failure. But Corning has had it on display hanging there since 1951. I've seen it a number of times. It's really big and interesting to see that. So pouring the molten glass, they did a second attempt at pouring the test blank, which was successful. And then after nearly a year annealing time, the disc was finished and taken by train to California. But historically, the creation of the disc and its journey across the economically depressed nation, going back to the depressions in the 20s, captured the public's attention. And the famed radio commentator Lowell Thomas called the pouring of the disc the greatest item of interest to the civilized world in 25 years, not excluding World War I, which it was at the time. So I'm going to go into a little bit of astronomy history here, because some of the astronomers know these guys and have visited Stellafane. But James Harkness, he was actually the past governor of Vermont. In 1910, Harkness was a longtime friend and enthusiastic amateur astronomer, introduced Russell Porter to astronomy. Russell Porter is another very famous person up there in that area. And this fueled Porter's interest in astronomy. So Harkness had designed and built an indoor observatory. So observatories don't work well indoors because you have poor seeing when the optics are, warm, and then they go out through the open window, and then you get the waves and you get bad seeing. So he had designed a telescope optics outside of the observatory where he was viewing from a heated room, so he had the best of both worlds. This inspired Porter to create a similar observatory at his home. And if you've been to Stellafane in Springfield, Vermont, you may have likely visited the Hartness house and actually toured this. It actually goes from the basement of the house out to the observatory. Now, Russell Porter, he was born in Springfield, Vermont, right where Stellafane is, in 1871. He was the first president of the Springfield Telescope Makers Club at its founding in December of 1923. Again, back in the Depression years. In 1926, in July, they had the first Stellafane conference. I think right now they're up to about 85 because they stopped it during the war and things. But it's the 100th year of Stellafane. Many of you have heard of him in association with Stellafane or Stellafane, as it was originally known, which means shrine to the stars. He designed and helped build the famous Pink Clubhouse on Breezy Hill in Springfield, Vermont. His family actually owned the property, which he let them use, and then he sold the property to the club for $1. He also designed and built the Porter Turret telescope on a large rock on top of Breezy Hill, which is right here. In 1928, Porter met with astronomer George Hale, the one who had the vision of making the giant telescope. And Hale was in early planning stages of installing a 200-inch reflector, the world's largest telescope at the time. Porter accepted Hale's offer to assist in the designing of the 200-inch telescope. So now you see the connection. Try to draw connections here. So this is the 200-inch Hale reflector on Palmer Mountain. It was known as the Great Eye and was the largest telescope of the time. Actually, it was the largest until I think somewhere in the 80s. But this is the picture, and this is his rendering. So now we'll talk about Edwin Hubble. I'm sure you've heard of him as well. He used this largest telescope in the world for his amazing work with extragalactic variable stars, which we call CHEPID now. In particular, he was looking at NGC 2261, and all this led to the development of the theory about redshift, which again was star 3C 273, and the expanding universe theory. So all this came from that same piece of glass. It also aided in the discovery of quasars and the first known brown dwarf star. So that's Edwin Hubble. There's another guy I think you may have heard of, Albert Einstein. He actually viewed through the 200-inch Hale refractor as well. So it was quite famous. So jumping around a little bit here, we're talking about casting the 200-inch mirror. They used over 65 tons of what they call batch, silica, glass, and things like sand, and they poured it, needed for the 200-inch disc. They had to heat it very slowly, so they heated it at 400 pounds an hour, and it was put into the melting tank. And then on March 25th, in 1934, the pouring began. And through the day, molten glass was transferred from the melting tank to the mold. So they got these huge ladles, and they filled it up. They poured it out of the crucible into the ladle, dumped it into basically a wheelbarrow, rolled it over to the other thing, and dumped it out. And it was, glass was cooling and falling on the floor, and it was like quite the spectacle. I saw a silent movie with it. It was pretty interesting. The mold was transferred from the beehive and placed in an annealing oven for 10 months to cool very slowly. So they couldn't let the glass just cool because it would crack. So they had to keep it heated and cool it very, very slowly. It took them 10 months to cool that mirror. But it was successful. So finally the last ladle of glass was poured, and the newspapers told of the making of the new eye for the world. There's an actual photograph of one of the workers at Corning measuring the beehive part. Shipping the mirror across the country. After 10 months of annealing, the 200-inch mirror blank was ready to be shipped off from Corning to California. So they couldn't just put it in the back of the truck. So they actually fabricated a special railroad car and they built a special case to hold it upright as it traveled across the country. It took more than 2 weeks, and because they were very conscious of the possibility of having accidents, it was only done during the daylight hours and at speeds of not exceeding 25 miles an hour. It was very, in the news, it was very much the talk of the town, and it made numerous stops along the way with much fanfare in each city where it stopped. So this is a picture of the workers finishing up the container that would hold the mirror. And there's the actual photograph of the crowd of people there at the railroad yard watching them load the big crate mirror on top of the railroad car for most of the trip. So the disc remained at Caltech's optical shop in Pasadena, California, for the painstaking process of polishing and grinding. So they had to take this blank they call it a glass blank, and make it into a polished surface with just a perfect curvature. And so the progress of this slowed as the nation became involved in World War II in the mid-1940s, early 1940s actually. But the disc was finally installed in 1948 in the Palmer Observatory, where it remained the world's largest effective telescope until 1993. There's the date I was trying to remember. And it aided in the discovery of quasars and the first known brown dwarf star. The telescope is still in use, although bigger telescopes now exist in places like Keck Observatory in Hawaii. All right, so now, this guy you probably haven't heard of. His name was A. Wallace Everest Sr. So Wally Everest was recognized as the most knowledgeable telescope maker of his time. He taught and wrote on the topic extensively. He had many articles in Scientific American, and he wrote the 2 classic amateur telescope making books, Amateur Telescope Making and Amateur Telescope Making Advanced. He also built the famous Everest Pump telescope, housed in the roll-off roof observatory in Tupper Lake. I know some of you have been up there to see that. There's a little pamphlet over there about that famous telescope. So what Porter actually did was he aided in the design of the honeycomb cell structure, which made the possibility of making castings successful, large castings. So the mold was sealed into the beehive, and that was fired with gas to maintain a uniform temperature during pouring, keep everything hot and molten, and keep everything the same temperature. Because if you have like 400 batches of something, it's not going. Some of it's going to be cold before the last batch gets in. Again, transporting across the country to California went by truck and by rail, mostly by rail, but parts of it had to be transversed by truck, especially at the end going up the mountain. Specially created mirror made slow and cautious trip from Corning to Mount Palmer to Palmer Mountain in California, and that's a little scale model of the railroad. So that mirror over there in particular, about 6 20-inch mirror blanks. So according to written records and word of mouth and historical evidence, there were about 6 20-inch mirror blanks poured along with the 200-inch Hale mirror. So along with that 200-inch mirror, they took some of that same glass from the same batch, and they poured 6 test blanks. One such mirror is at Caltech. They're the ones who finished the mirror for the Mount Palmer. And our second one is at Corning Community College, which is the college right where Corning glass is. But tonight we have the third mirror casting, which is right there on the table. This is the partially finished 21-inch disc of annealed Pyrex. It's 4 inches thick, and the disc has been ground to approximately an approximate curvature of an F5. And the edge and the back are unfinished. That's why you can see some of this That's actually on the bottom of the mirror, and this is on the side. The paper trail, there's a 5-page agreement, which is also a photocopy of it's on the counter there. The mirror blank was given to Wally Everest by his wife. So the original person, Wally Everest Sr., was given to his wife, Mary, on Christmas of 1936. So how did this happen? Well, Mary made a request to Wally's close friend, Russell Porter, who we talked about earlier, who was involved with designing the Mount Palomar telescope. And it was a gift for her husband. So Porter made the arrangements for the acquisition. So that's how Porter ended up with one of the 6 test blanks. So after Wally died, the mirror blank was passed on to his son, Wally Everest Jr. And this 3rd blank was ultimately donated to the Adirondack Observatory in October of 2006. This nonprofit entity and the Everest family will mutually benefit, and I'm quoting, from the publicity and educational experiences stemming from the construction and use of this historical materials. So they gifted it to the observatory. They had things in there about they have to have it for 15 years and all that. It's all in that 5-page document. So Kopernik has a sister organization. It used to be known as the Adirondack Observatory. Now it's called the Adirondack Sky Center and Observatory in Tupper Lake. Here is a picture of the original sign with the roll-off roof observatory and what was the field. Here's a better close-up with the roll-off roof, where the roof actually rolls off on the railing back here and exposes the telescopes. Here you see the telescopes opened up. And this is a picture of Carol Levy when she was younger, who we'll talk about next slide. So the ASCO and the Adirondack Public Observatory. So Carol Levy, the past president of the APO and ASCO's board of directors, has cared for and guarded this valuable asset since 2006. She plans to house this mirror in a display when their new buildings are constructed at their Tupper Lake site. So right now they just have the roll-off roof observatory. They've done some land preparation, but it takes a lot of money to do this stuff, and they're still raising money. But this will be the new building, and here's the new observatory in the background. Future plans are for a science building, which will also include a planetarium and a second observatory building to house the 24-inch plane wave reflecting telescope. Currently, their roll-off roof observatory, named in Carol's honor, houses the historic Everest Pump Telescope, a Celestron C14 Edge HD SCT, a Me 12-inch SCT, and a Teleview refractor, along with some smaller scopes. And that facility is open, just like Kopernik, on Friday nights. There's only clear Friday nights. And how did they end up here at Kopernik? Well, I stole it. No, not really. It's pretty heavy. If you try it takes 2 people to carry that. Years ago, when the APO was just starting in 2003, Carol visited Kopernik Observatory and Science Center, right where we are, and after an extensive investigation of public observatories, Carol decided to try and model their new facility after us here at KOSC. So she actually met with me to discuss her plans, and I became a member of their advisory board, and KOSC adopted the APO as a sister organization. So we kind of work together, help each other, support each other. Other KS members, Kopernik Astronomical Society, I'm sorry, I skipped a sentence here. George Normandin, the Kopernik Astronomical Society president, and I are charter members up there. And there are other KS members are also currently members there now. Over the years, George and I have helped teach at their astrophotography concourse a number of times. So while speaking to Carol, I was talking to her, I'm going up there next weekend to help with the conference. But while speaking with her, I mentioned that this was going to be Kopernik's, would be celebrating their 50th anniversary in 2024. And she thought, wow, I had this mirror. Wouldn't it be great to have a display? Because she's had it literally in a crate, not having a suitable place to put it. So after she received their board's approval, she offered to loan the mirror to us for the year. And we're in the process of building a display for it that will be developed to explain how this was created and explain the mirror itself. There are the credits from the internet, from Astronomy magazine about stellar and then from Sky and Telescope, and then one about quasars, and then Adirondack Public Observatory, and then Carroll and Wally Everest for the information. All right, so yeah, I got out in time. Any questions? All right, so you're free to look at it. Please do not touch it. Dave spent a little bit of time this morning cleaning it up. It really wasn't too bad, but there was some of the dust, the remnant from the edge stuff on it and stuff. But the acid in your fingers will actually etch into the glass. So even, even light bulbs, you really shouldn't touch the light bulb. You should really use a rag or something because it puts a weak spot. Not so much in that bulb, but in that bulb there that's like $300 in the projector. You don't want to do that. Okay? Thank you very much. All right, so next we're going to have a little break, and then there's going to be a lunch. Music will be playing. Then we'll have, during lunch, we'll have an astronomy roundtable, which we would encourage anyone to come and talk and just talk about your club and things that are going on, what you're doing, what problems you have, what other solutions someone else might have. Okay? Thank you very much.
Good afternoon, and welcome to the afternoon session of the AstroFest 2023. This afternoon we have Dr. Werkman talking for us. He'll be talking on electronically assisted astronomy. He made me change the title because mine was less accurate. Or as he puts it, astronomy for the masses. Keith, whenever you're ready.
And you can hear me? Oh, you can hear me. I can hear me. Is it too loud? Should I put it a little lower? Okay, has someone any feedback or, well, you're in charge, you know what you're doing. So, wow, cool. I guess I'll stand at the podium. Hello. Hi, Keith Werkman here, part of Kopernik Astronomical Society. I get suckered into this talk by Art. Because we were at Cherry Springs, 4 weeks ago, whatever, you know, for this Black Forest Star Party. And with our other friends here and such, and I kept bugging him, saying, "Look at my phone. Look at his pictures I'm taking." I got annoyed enough and said, "You're gonna give a talk on this." I said, "Okay, fine." So here we go. So yeah, electronically assisted astronomy. I stumbled across this, I think, 2 years ago. Some gentleman from the club up north here in Syracuse was in our parking lot, and he had quite a large scope, and he was setting up, and he showed me how quick you can take pictures and show it on a tablet. I thought, that's really cool for outreach. So that's when things were kind of kicking around. So since then, several devices have been created, and even some newer ones are coming out, and they're just coming out. So we'll kind of touch on all of those. So EAA, basically attach a digital camera to a telescope. This is like imaging, folks, but it's usually for faster imaging, and gives you an average picture that is good for outreach to show to the public. Types of EAA, we have classical, just real. I look at my friends here, and I know they've got some high-end rigs, and they work quite well. And they're also, we were imaging at the same time, and they're showing me in their tablets. They're much nicer pictures of, you're doing Rosette, I think it was, or what were you imaging? It was Rosette, yeah, Nebula. Looked really good. And mine, it was okay, it was getting there. I'll show you the little one I have. So basically, there's kind of two angles to this. The big rigs, which can cost, but they're very versatile, and the kind of off-the-shelf ones you can buy now, which are kind of neat. That's what I'm calling the enthusiasts. I'm sorry, the novice ones, rather, easy to use. And there's a couple out there, Vionis, I guess. They have the Stellina and the Vespera, which have been out initially for a couple, 2 to 3 years already, I think. Unistellar has the EV scope, about 2 years also. And recently, as of this March, I think, a company called Dwarf Labs has the Dwarf 2. I'll show you what it looks like. And then there's another popular one called ZWO, who makes a lot of imaging equipment, which a lot of our people in our club have. Which have a lot of components that are all linked together quite well, like an ecosystem. And they have one called the SeeStar 50, which is coming out. And it's been reviewed by some YouTubers. You can look at it online. And we're all waiting to get ours. I mean, Mark, you said, what did you say? You said that we all ordered from High Point Scientific, right? And they have how many? 1,200. And you're going to get yours maybe at the end of this month. And I ordered a month after you, so I'll get mine in December probably. But they're coming, so, and some reviews, some pictures I'll show you look pretty darn good. So, okay, just a quick recap. We look at stars with telescopes. We have the visual scopes, right? Your refractors, your Cathay optics, and your Newtonians there, your reflectors. And as you see in the lower corner, I don't know if can I use the mouse to point like that? So in the lower corner, you see a standard imaging rig. Requires your tripod, your OTA, right? Your guide scope. Your focusers, if you have filter wheels, you got your camera, you got your laptop here. It takes 5 minutes to set that up, right? No, wait, it takes a while to set that up. And of course, here's components. I said your guide scope, cameras. People in our club have one-shot colors, which is really nice, versus using filter wheels and taking CCDs or whatever, and merging them together later with multiple colors. Portable power. There's a lot of stuff involved. But, you get good pictures, right? So it's part of the hobby. A lot of people play this game because it's fun, and then they like to learn their gearheads. They like to play with the technology and stuff, and it's kind of neat. Let's see, compared to traditional scopes, they have modular parts. They're purchased separately. You can swap things in and out. I have this camera, and I have a one-shot color camera. I have a different sort of finder I'm going to throw on this type. For focusing, use a Batinoff mask. I have automatic focusers, all sorts of stuff you can get. But, of course, it takes time to set it up. And if something breaks, you got to troubleshoot in the field at night sometimes. That's a little stressful, I can imagine. But, you know, you have everything you need. But so just to, I did some slides with some background. Let's see, a few tools needed. Like I said, you need your scope, your computer, various components, plenty of camera vendors such as EWO and others out there. There's a bunch of chips here. I'm not familiar with all these chips, but I'm sure. Well, what's your one-shot color? Is that this on here on the ASIs? Okay, so these are high-end set. So these are like full frame kind of things, right? It's your standard DLSR frame, but they're large sensors. In these devices, no, we're like an eighth that size probably. But either way, it does take time and effort to set these suckers up. What do you need for a basic imaging rig? If you will, you have a telescope, your focal reducer that takes and flattens out the field so you have no curvature at the end. Motorized mounts, of course, for tracking. The camera, electronics. We just talked about different types of cameras you can get, either CCD or either monochrome or full color. Focusing aids, either you mask you manually with a batten-off mask or actually focusers built in. Deep sky guides are good to have, like your what's our free one called that you guys use for an astronomy program? Astronomy, I forget. Anyhow, so we have multiple ones you can use. Some are free, some you pay for. Yes, yeah, Sky Safari, for instance, we use that and stuff like that. I just did a little slide here talking about the types of cameras. I kept saying CCD. This is what I guess we have in the 20-inch. These are true, highly sensitive cameras. But of course, for more the consumer side, CMOS has kind of emerged. And CMOS, nowadays it's a little cheaper to make and stuff, and they've gotten better. And they have a little less noise, not as much like CCDs, I guess. But bottom line is, most of the chips are going CMOS now. They're more affordable for these smaller devices. One-shot color, for instance, any filters, so you can play a lot more games that way. So CMOS is where things are kind of going for these, at least commercial grade or consumer grade cameras, which you buy either for big time for your big rigs or these smaller self-contained rigs. And for instance, I just showed some quick pictures here of some people who actually have the big rigs, if you will, and they can actually image with these cameras in short times and still get pretty good imagery. So you have, I guess, M42 over here, right? I think there's the Orion Nebula, right? With a 60 millimeter refractor, so you got a lot of light gathering, 60 millimeters. And to the right side, we got NGC 1499 California Nebula, which is big and long like that. And sometimes you have your nice scope. You kind of focus. It's hard to get large objects. With this one I'm going to show today, which I have, I took a picture of the California Nebula when we were out at Cherry Springs a couple weeks ago, and I got more of the image because it's just a wider field. It's a smaller, it's a smaller lens and just more of a wide angle. So just plus and minuses of things you might want to use them for. This is just showing, here's the whirlpool. Looks quite nice. I'm looking for timings. Let's show timings. And a lot of people. Rick, what's yours? Does it stack? Does it do live stacking when you take pictures? And then you also have FITS files, right? So it does a stacking. And it makes a JPEG, or does it make a stacked TIFF?
The JPEG is produced from the image that you take to display
on your pad, on your iPad. Yeah. So that's what these rigs do. And ironically, what the big rigs do, even these smaller rigs are starting to do the same thing. They're taking your JPEG, which shows up on your phone, or on a tablet. You see here I have it turned off, but I'll show you in a tablet. There's a picture online. JPEGs, and they'll do, I guess, even stacked TIFFs, I think, which means kind of process. And then the full-out FITS files, which are the official data files, which you can play games with each snapshot, and you can merge or mask and throw out junk, and then you post-process these suckers, too. Here's a nice one of, there's a Veil. That's what one of the ZW ASI cameras. It says 16 stacked at 60-second exposures. The advantage of the big rigs is they're polar aligned and they track, so you can take long exposures if you got your alignment quite nice. These little guys are alt-as, right? So they're not going to track that well. But comparisons, and sometimes not that bad. So here's our buddy Nico. He was talking at Cherry Springs 3 weeks ago, and he's got his YouTube channel, Nebula Photos, and he asked, "Can I beat a robot in astrophotography?" So to the right, you see the Vespera. That's one of the newer flavors that came out of Biona, and it's about $1,500. And then he has a rig he built to the side here, 16, I don't know if it's a 80 millimeter, what do you got there? And he's got all the goodies on there, the ASI airs and all sort of stuff in a tripod. He says it's similar in price. I think it's probably a little more, but he compares the pictures, and lo and behold, the top is his rig, the bottom is the robotic telescope. Ironically, they're taking shots of a horse head, quite nice. You see this streaking here. That stuff does kind of exist, I guess, from noise on chip. And I learned as I'm doing, because I am not an astrophotographer. I'm the novice saying, well, I can sort of start playing the game a little bit here with these new robotic telescopes. I've learned that evidently this is some noise on chip like that, which is something called dithering. And if somehow you take a picture, and the next picture move a little bit, and then come back and move around, you kind of dither. When its stacking occurs, the stacking says, what's this weird random stuff, this noise on chip? It ignores it, and it stacks the signal, lines up the stars and stacks the signal. So this stuff goes away. So a lot of the YouTube reviewers are saying this is something that these companies should be trying to look into. And indeed, I've got the Dwarf Labs, the Dwarf 2. That's a Kickstarter project, ironically. And they're very responsive to what reviewers are saying, so they're going to try to do something like that. I've heard that the new ZWO SeeStar 50 coming out is going to also have something like that sort of maybe in there too. And Vespera did something like that for when they do large mosaicing. So new software features are coming as people are complaining, and I got to be like the other guy because my scope's a few $100 price difference, so they're all going to play the game. So as time goes on, it's all going to get better, which is good for us. So just to show, it's not that bad. So these little toy scopes, robots, are not too silly. How do you pronounce this guy's name? Queeve? The lazy geek. He's another guy I stumbled across while doing this research. Because he reviews all his robotic scopes as well. Of course, he's what city is he in? Tokyo. And how bright is Tokyo? It's like being on the sun, right? And he does astrophotography with these scopes, and he gets really good results. Very just impressive. Anyhow, he said, yeah, you can sort of, and this is just before the Dwarf 2 came out. He says, I'm going to make a small robotic scope. I'm going to compete with these guys like the $15,000 blah, 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 Vespera and stuff like that, or $3,000 or $7,000 big ones. Stellina when it first came out 2 years ago. So he has this. So he stumbled across a nice Skywatcher tripod, and so he's got the tripod. He's got this guide scope, 50mm guide scope, an ED, which he's using for his telescope. He's got a ZWO camera here, the ASI 178 MC. That must be color, I'm guessing. I don't know. He got a Raspberry Pi, mobile battery. Some cables, Stellarmate app, and Sync Scan apps. These are free. Well, I guess you should buy them for $5, but they're apps you can get cheap on your devices, and they actually control these suckers. So you can build your own kind of robotic telescope if you want to for like quick imaging like this, which is kind of cool. And then, of course, the Dwarf 2 came out. And he said, "Oh my God, competition." So when you go back to these little scopes, basically they're low cost. You start taking astro and other pictures right away, and you have instant gratification. So if I'm going to start playing some astrophotography games, I walk out, and in 3 minutes I'm set up and I'm taking pictures. People with big scopes, they take more time than that. That's what I'm going to say. So it's a trade-off. Like I said, and then for post-processing, a lot of these YouTubers are using free software called Cyril. It's not quite your top-end PixInsight, which I guess costs thousands, I'm guessing. It's the program for all imagers. It has tons of stuff you can do with it. But there's a lot of low-cost free stacking tools and stuff like that. And Cyril evidently has got a lot of processing, which people have used for pictures I'll show you from these little robotic scopes. And it looks not too bad. I own a Dwarf 2. I spent, well, $450 is the base price. I bought a couple extra features, like a secondary battery, filter holder, 2 solar filters, and 1 light pollution filter. So I paid $550, $100 more. So that's out as of February, and I bought mine like in beginning of summer, probably June, I'm thinking, right? So I look at Art, because I bugged you when I first got it and I came up here. It's probably just about then. And I basically said, we all ordered the ZWO SeeStar 50 too, because that was $399. How could you not, after seeing these other ones and being a little bigger, better from a brand name you'd know. And so I got this one for, I said, well, I'm going to get it now, and I'm with the Scouts and our Baden-Powell Council. I said, well, I'll help out with the Astronomy Merit Badge, and I'll take it up there, and we'll set it up, and it's easy to carry in a backpack. I don't know if you've seen it. Here's the bag it comes in, so that's kind of heavy. And I had a case. I spent $9. I bought a tripod from Amazon. And when I want to image, it's really quite difficult. Oh, here we go. Just pull out that's it right there, and then you know, you just throw in a tripod and off you go. So for ultimate ease, this is the easiest one and the cheapest one that's out there. So I'm ready to go. And then, of course, I can turn it up and it can look at you. It has 2 lenses on it. I'll show you more details. And then, of course, I got this extra battery. It lasts about 4 hours of battery, so 2 batteries, 8 hours. But I realized that's a hassle, too. So I have another battery pack with a cable, USB adapter. I plug in there, and it runs all night long. Comes with a tripod, kind of small. But, you know, when I'm out in the woods, I have another hobby, ham radio. I kind of sit out and talk to people in the woods, and I set this on top of my car, and it takes pictures while I'm talking to radio, and next thing you know, I've got data. I've imaged like North American Nebula, and I got a 2-for-1 in my hobby there. So that's kind of the whole shebang. And of course, that's an app. So kind of neat. So oh yeah, there is the SeeStar. I'm sorry, the Dwarf 2. This, like I said, was a Kickstarter, and it's made by they contracted some manufacturer in China, and they did an awesome job. Like I said, with this, I also have this adapter. You can see that. That's this thing here. And I got 2 solar filters in there, so I can actually just kind of magnetically throw it on there, and there you go. Or I can put other 1.25" filters on. It came with a little Nebustar or something like that, a light pollution filter. And basically, it has two lenses. It has a telephoto and a wide angle. So I said, with the 1,000,000-to-1 adapter, I can look at the sun and take pictures of sunspots and stuff, which is kind of cool. So this device, you can play not only at nighttime, but it takes pictures in the daytime. It's got some AI algorithms in it to actually track things. So if you're a bird watcher, you can click it on birds, and as the bird flies, you can take videos, 4K videos at 30 frames per second. And it throws to a default 64 gigabyte memory card. You can put like 512 max, I think, in there. Not too bad. And then Queeve said, well, you know, he had a chance to review the SeeStar 50, which is coming out, right? And but they're kind of delaying it because I think they realize the competition has nice software features, and they didn't have those software features. But over the last month or two, they're adding all these software features in, like autofocus and a big catalog of images to look at and stuff like that. And so Queeve here is like, he reviewed this. And this is a snapshot in the video. He goes, well, I don't know why I've got these large imaging rigs when these things can do pretty much what I can do too. Maybe not as good, but you know. So he's very impressed with what it can do. And as you can see, this SeeStar 50 from ZWO, it folds up nice and small. It's going to probably be bigger than a Dwarf 2. As you see, it's nice and thin and narrow, like a book, right? The SeeStar will be like 2 cases big, so it's going to be bigger. And you have to buy a case for it. You know, it doesn't come with anything pretty much except a filter, I think, as a solar filter. And internally, it's got a filter built in for some light pollution, where this Dwarf 2 has no filters. You add external ones. So I think it's a little more flexible. The difference is very small aperture, 25 millimeter. Everyone else is like 50 millimeter and bigger, and have better focusing. So here's some features of the upcoming ZWO one. Fully control your imaging. It's a 250 millimeter focal length with a 50 millimeter lens versus the Dwarf 2's 100 millimeter with 24 millimeter diameter lens. Basically, Dwarf 2 is good for wide angle. I guess you'd say a large field. You can take North American Nebula. You can take California Nebula, Milky Way, stuff like that. But it's quite, well, not that big. But things like Pleiades fits in the field nice with some stars around it. With the SeeStar, you get the Pleiades, but you have nothing around it. So it zooms in extra, you know, twice as much. So it has built-in Wi-Fi and Bluetooth. That's the new one coming out, and this one also has Wi-Fi and Bluetooth. Built-in sensors. This guy knows things. Has filters. Like I said, we have a filter holder in Dwarf 2. There's a built-in one on the SeeStar. Oops, they have auto-focusing. They have go-to and tracking. Because the Dwarf 2 is more of a wide field, you can't have lots of tiny images like the cat's eye. It's not in its catalog, right? You have things like the bigger stuff. Most of the Messiers are in there because, you know, binocular optics, right? Big things. And so it does a pretty good job. Things like, you know, M27, the dumbbell, it's kind of small, where with the SeeStar it's going to be nicer, field frame a little bit bigger. So image enhancement, they have live tracking, they have live stacking too, which is kind of nice. Just minutes to you in the universe. It does not, oh, that's a mistake. Currently does not save FITS files. Turns out the latest software on a SeeStar 50 from ZWO does all 3 flavors, just like we talked about. It'll do your JPEGs to your phone or your tablet, to the app. It'll do your TIFFs, I guess they're stacked, which you can process, or it does all the separate files called FITS files. And Dwarf does that, and the SeeStar will do that also. Internal battery for the SeeStar 50 from ZWO will be 6 hours. Dwarf 2 is 4 hours, but you have 2 batteries, so 8 hours. There's no replaceable battery in the SeeStar, but I hope you can externally power it. Otherwise, you're set, and then it runs out of juice. So I'm not sure if that's gonna be an issue. They got to do something. All I know is with the Dwarf, I have a little tiny battery pack in my backpack. I was gonna pull it out. I forgot the prop to show off. Sorry about that. I'm bumping the microphone here. And you get your standard battery pack, and I've got a cable and this little hole in the front for charging. I lie, it's on the side, and you plug it in like that, USB-C, and next thing you know, you're off and running. And now it recharges the battery inside the unit. It's charging, and if you turn it on, you see there's a little light there. It's charging, blah blah blah. So I can run that. Or I run that each night, right? At Stellafane or Cherry Springs. Didn't go to Stellafane this year. So anyhow, let's see what else it has. 6 3-lens professional opera chromatic. Oh, the ZWO has real Apple lenses. The Dwarf 2, I don't think it does. More acro. But so it's got a good set of lenses. Landscape night sky imaging. Turns out that this guy, the Dwarf 2, will actually take daytime pictures, like I said, and such like that. And matter of fact, if I aim it at me, I'm talking. I probably show it on the tablet over here. So it does its thing, and you link up to it by Bluetooth or Wi-Fi, and then you're off and running. The other nice thing is panoramic shots. So with daytime, so this is more commercial. You can take some nice deep sky images, but if you're into bird watching, you can turn on daytime, aim at birds. Let's see just a heck if I can turn on the tablet here and I gotta show you. I had the app running, of course. It says Dwarf Labs, says connect, hit the connect button. It sees the scope as C18630, so it links up to it, and hopefully it shows up. And then you have 2 views. You have a wide angle and a telephoto view. Your astronomy views are certainly telephoto, but wide angle, you can do terrestrial stuff. You can take pictures of things. Has a joystick. Connect already. Sorry. Of course, live demos are always more fun than pre-canned ones, right? So there you go. That's it. You can see a picture of me in the upper corner. If I hit it, it swaps. That's the wide angle view. Here's a telephoto view. You can see my hand moving in there in the corner like that. It's got a little joystick in the corner. You move up and down and around. Things move around. It's got different modes. It's got a burst mode. It's got time-lapse mode. It's got photo mode. It's got video mode. It's got panoramic mode. It's got astro mode. And it's got astro dark mode. So you can actually take pictures of like I said, things moving. It's got some tracking algorithms. They claim AI algorithms, which actually let you track things. Let's see if I put it there. If it actually, yeah. Oh well, you get the point. And actually, Queeve did some shots, and since he knows what he's doing and he has Pix Insight and knows how to process the heck out of these things, those pictures look pretty good from the SeeStar 50. Not bad. I mean, it's pretty. Sometimes you have bloated stars, but some of these stars are not bad. And of course, it all depends on your processing too. And I've learned something as well. You take these pictures of dim things, you don't see them very well, but then you take a histogram and you just kind of stretch it out. All of a sudden, the data emerges. It's kind of cool. So I'm learning about astrophotography by having a simple entry-level device which captures data, and I can post-process and learn all astro stuff in the back end. So in my mind, getting into astrophotography is like cut in half because I have simple, and I can now play these games and learn from my buddies how to do this stuff. Here's what I showed before. This shows this is this one here, the Dwarf 2, with a telephoto lens, right? He's got a picture of them, and he's showing the. Well, you get the idea. And from their website, they show these pretty awesome shots. I assume people really did these from the Dwarf 2, but there's very sharp stars there, so I'm sure there's a lot of post-processing done here. And you can take pictures of birds and other stuff like that too. So now I'm going to just go into how much time I've left here. Just the background robotic telescopes. This Jeff Purdue, in December 22, from an astronomy club in, I think, DC, had a nice presentation, so I blatantly absorbed it. I give him credit. He talks about robotic scopes. That's the Vespera right there. Just like we said before, you can build your own system. You can stay in your own ecosystem. In this case, ZWO. I see a tripod and a special mount. I guess that's a good mount, right? I don't know. Maybe you have that one, Rick. I don't know. You have to the left, you have the ASI Air, which is your Wi-Fi integrator kind of thing. What's the EAF? Is that a focusing? Oh. To the right's a camera, I know that. And to the middle must be a little scope or a little guide scope right there, I'm guessing, right? So you get all those things put together. You're very modular. If you're within the ecosystem, it's probably worthwhile. Everything works better together, and it's probably cheaper to package and work properly together. So there's less chances for things breaking in the field and more troubleshooting, I guess. Pluses and minuses. Well, the robotic guys are simple and lightweight. Traditional, a lot of versatility, and you can reuse components and swap things in and out. But, certainly robotic stuff is cheaper and should be good quality. We'll find out. Certainly the traditional stuff, you buy quality components, they're going to last, and you can sell them and stuff like that. So I see these robotic telescopes as EAA scopes, being as something that the public's going to grab into and get more into astrophotography, because we're up here on Friday nights and people walk up with their cell phones. They're like, I want to take a picture of the moon. So we put up to our F12, a super planetary scope, and they sometimes get a good shot, right? But when I get into this stuff, it's going to be interesting. And once again, rolling back, I said this earlier before the talk, when you go to Cherry Springs, over the years, we were all visual observers, and you see the Valley of the Dobbs, all nice scopes out there, and people late at night. Now we're in the same Valley of the Dobbs looking down, and we see all these tripods and glowing lights, and people are sleeping, and where are these people? And these robots are taking pictures of the sky, these rigs. Because they want to take, multiple exposure, many hours to really get lots of data to get really intense pictures or faint objects. So it's kind of interesting. And what I'm seeing, I think, is more people are going to be buying these things at the $500 entry level or $450 entry level. They're going to start coming to Cherry Springs. Hopefully they'll stay on the public side. But if they make it in and buy into the semi-professional side where we kind of hang out, it's going to be less spots for us. And it could be interesting. I see a lot of astrophotographers just getting something cheap like this because, some guys are already with their big scopes or one or two rigs, $20,000 a rigs, whatever, they're taking pictures. They might want to have something on the side taking a wide angle view of the same object. Some aren't doing that with separate cameras. If they have something like this, they can take multiple pictures quicker and get more stuff to kind of play with as well. So I see this as an extra tool in the tool belt for the astrophotographer if they want to have wide field type stuff as well. One of the other things these scopes have is go-to and also plate solving. The Vespera, the earlier scopes had a bubble for leveling it out to figure out where you're in the sky. These guys, I put it on my roof, I put it anywhere, I knock it over, I say, go find it. It starts plate solving, boom, 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 boom. I know where I am. I guess it's talking to your phone, so it must be using GPS maybe out of your phone, so it knows where you are for that long, and then it plate solves. It takes about 15 seconds. Yeah. At Cherry Springs, it's very fast. Here it's harder. It goes around the sky trying to figure out stuff, but when it's really dark, it takes snap 1, snap 2, snap 3, I'm done. It's like, oh my God. It just blew my mind. And the funny thing is, these are alt-as, so when you take pictures, let's talk about stacking and stuff. It's sky rotation. So one of the things that someone said on YouTube, I said was, well, why don't you get a cheapy tripod like this? Why don't you put a wedge on it? Well, I can't put a wedge on it. How am I going to, it's going to be top heavy. I can't do it. Oh, look at that. There's a wedge. So you take a tripod, aim it back, and I'm at north right now, and close enough, and all of a sudden it goes this way, and it goes this way. So there's your polar scope. And sky rotation's a lot less. And it doesn't matter. It seemed to work. It's like, I don't care if I'm level or whatever, just plate solve. I was all happy. Like, I'll be darned. So, I'll be darned. So anyhow, you see most of these guys, they are alt-as, and they're not, you can't play that game, so to speak, right? They have their own tripods. The very first one to the far left was the $7,000 good old Stellina. Came out 2 to 3 years ago. I told people in the club, they said, I'll never be any good. So I don't know, it looks pretty cool. Then the next one was the Vespar from the same company, Vespera rather, I'm sorry. And that's the one's about $1,500 in that range. It's quite nice. It's a 50 millimeter scope, but now it's ZWO's SeeStar 50, same sort of scope for $500. Oh, well, it's 1/3 the price. That's even cooler. So there you go. Well, the introductory price we paid was $399. It's even better, $400. That's quite nice. So I'll have to see. Off to the right here we have the Unistellar. They had several scopes. I think the EV scope 1 or 2 this might be. They're for the 4-inch reflectors, but they have a very large, central obstruction, so I don't know. But they suppose they take better pictures, but they're in the $5,000 range. Some you get as low as $2,000, I guess. I don't know. Then you got a little Dwarf 2 in the corner here for the $450 to $500 range. Oh yeah, here's prices. That's right. So this is currently off of Amazon. Vespera, not bad. When the guy's talking, he talks about this one. If you had the full, if you get the 490, well, what's 450 now? It's, yeah, 450 that range. That's the basic device, carrying case, little tripod you see there, a battery, and a memory card. But for $100 more, I splurged. You get the solar filter, the 2 solar filters there, the light pollution filter, and an extra battery. And so that's kind of nice. So that's what I did. Yeah, this is a good price, $2,000 here. Normally like 5,000. You know, they're up there. The initial Vespera was Stellina was 7,000 first came out. Now it's down to 4,000. They realized the competition's coming. And here's our SeeStar 50 from ZWO, a well-known brand of fantastic components that imagers use. And so they've got an entry level that's stuck up the lower end of the market too. So we'll see how this all plays out. The thing is with the big scopes, like I said before, you actually can track and take lots of pictures for longer exposures. So to the right here, 5-minute subs, 60 exposures. For this, field here, the little guys with the Alt-Az, they're taking short and lots and stacking. So 10-second subs, right? Lots of exposures. We get the same sort of stuff. And then you get the field rotation. Unless you cheat a little bit and play this wedge game, that's kind of nice too. Maybe you can put those on a wedge, but they might tip. I don't know. So that's one of the other advantages of the Dwarf too. And most of these scopes will take max 10 seconds because around 10 to 15 seconds, you can do that and get away, or even 20 seconds without sky rotation, maybe up to 30 seconds before you start seeing things rotate, I guess. The Dwarf 2 maxed out at 15-second exposures, so you can take half the exposure that these other guys take and get the same sort of data. But of course, the field of view is wider versus more focused with these guys, but it's just nice to know that there's that's kind of their snapshot, so they eliminate as much field rotation as possible. There's a Vespera. As you see it, it folds up and it flips out and stuff like that. There's some specs on it. Focal length is 200 millimeters. The Dwarf 2 is only 100 millimeter focal length. That's 25 millimeter aperture. This specs right here from the earlier Vespera is exactly what we're going to see with the SeeStar 50 coming out at 1/3 the price, right? It's going to be 50 millimeter aperture. It's going to be 250 millimeter focal length. It's going to be bigger actually, more focused in. Same Sony chip, the 462. It's going to be heavier, 11 pounds versus like, I don't know, 2 pounds like that thing is, or 1.5 pounds. So it all depends. If you do backpacking, maybe the Dwarf 2 is the answer. If you're doing a little more, bigger carrying case, I got a feeling the SeeStar 50 will be like twice as high as its carrying case, like 2 highs like that. So, and then, of course, there's always add-on accessories. The Dwarf 2 included everything. You're going to buy extras. This for Vespera has a bunch of filters right now. The SeeStar 50 from ZWO has just a solar filter and a built-in light pollution filter, which, I don't know, it's like going to impact other stuff. I mean, this has no built-in filters. It has external ones you add on. It also has an IR cut filter, right, built in. So, and it shows all the various add-ons and backpacks. We talked about, it says JPEG, your stacked TIFFs, and your FITS files for third-party processing with like Serial, which is a free package, or your high-end PixInsight, stuff like that. And also, the stacking software. I forget the name. There's a bunch out there, different ones you can play with. It shows physical setup. You can see the Vespera, has tripod legs, a balance, a bubble, and stuff like that. More components. It's just nothing. It's just one thing. You had to buy extra for a carrying case, and we'll put a nice waterproof case around it. That's going to be the case. I think this will be the issue. Also with the SeeStar 50, you'll have to buy some sort of carrying case for it. It doesn't come with anything, as far as I know. They've got apps. This is an example of just, and of course, SeeStar has both iOS and Android, like these other guys. I'm sure the demos of the soon-to-be SeeStar 50 tend to, I'm not sure if they're both. Must be both for iOS and Android. But they'll bigger targets, if you will, a longer list of targets, because that's a more of a focused scope. Examples, this gentleman from Tokyo took the pictures. This is actually, I guess, 33, which I took a picture of also. Mine didn't come quite as nice as that. I can see the bloated stars. And I think he post-processed also. Well, that's when he post-processed in PixInsight. So it's there, but then if you know how to play the game through processing, you can bring a lot more data, a lot more image stuff in the data. It kind of pops out, including color. Look at that, from nothing to more colorful like that. He took 31 here, his M31, Andromeda Galaxy M32, and M110 over here. You can see through the Alt-Az rotation, you have this weirdness, right? But if you just cut out your picture in the middle, hey, that's all you really want anyhow. So, one something, and this is more focused in at 200. This is the I think it's the SeeStar. Yeah, it's the SeeStar. So it's 250 millimeter versus the Dwarf, which would be 100 millimeter. So my picture would be smaller and more sky around it, but maybe you can zoom in, but he did that, and then, and I'm amazed, even like the Horsehead came out. Oh, I'm sorry, this is with the Vespera. This is the guy with the Vespera. Similar sort of scope, 200 millimeter, 50 millimeter lens. With the proper processing. I'm just amazed. So I can't wait to try mine, which will be 1/2 that size with this. Or with the SeeStar, it should be similar to this sort of thing. Rosette Nebula. Now this is huge, and of course you're missing you're missing it. Here's where the SeeStar wins because it's 1/2 the size. So this will fit in and have more star field around it. So for very large objects, the Dwarf 2, being only 100 millimeter focus, is focal length is actually will win. But then if you want more detail, you're going to lose it too probably. So kind of interesting, these pictures. Also, here's a dumbbell on the Vespera, which is similar to what the SeeStar 50 is going to be like. My picture on this guy, that dumbbell's half the size now. And he, of course, processed it so he can bring out all this nice detail. I've yet to learn how to process, but I'm sure if I download my images, either plug in directly with my USB cable or take the memory card out and plug it in and do a transfer over to the PC, and I start playing with these histograms, I'm probably going to... And there's also a histogram playing right on the app, too. Maybe I can see if there's more data in there, so see if it actually comes out with nice colors like that, the actual dumbbell, and the football kind of greenish around it and stuff like that. The Pleiades, here's how the 50 millimeter, 200 millimeter focal length looks. The SeeStar 50 will be a little more focused, I think, because it's 250 millimeter, a little tighter. Maybe you won't see as much. But on the Dwarf 2, you'll have much more stars around the outside. It'll look a little smaller. So I think this 50 millimeter is a better way to go. This 200 millimeter focal length, you get better imagery. The Dwarf 2, it's going to be wider. I guess you can zoom in, but it might be similar, but I think it's a little better with these guys. Orion Nebula, this guy took, in this case, the Vespera, and he actually had little gain. I can have a gain control from 0 to like, I don't know, 200. He has low gain here. He's in Boreal 7 skies are brighter than here. I mean, this is that Boston or something? No, I guess this guy really was. No, this is not the gentleman in Tokyo. This is another guy who I think either PA or DC. I'm not sure where his club is. But the point here is he took lots of integration time and low gain, so we can get the trapezium stars, so to speak, over here. Otherwise, get blown out. He said the Running Man nebula is over here. He can't quite get that. So in the next picture, instead of 3 hours, he went 5 hours and a higher gain. All the stuff is blown out. I can't see that here, but now you get the Running Man. Look at that nebula in there. See the legs and the head and the arms outreached. Pretty cool, huh? So, and these are with these robotic telescopes, which are easy to set up. So there's some, and this blows my mind. This is a panoramic that I guess mosaic that the Vespera does. Turns out the Dwarf 2 also does this. I haven't tried it yet. But they'll take a bunch of pictures of the sky, a couple rows, whatever you want, 4x4, I guess, and stitch them all together, make a big picture of a daytime image or supposedly a nighttime image too. So we'll have to see. But he shows, our M42 and on the far side, he's got the horse head and stuff over here too, and a flame. It just looks pretty cool in one giant mosaic. So I'm not sure. And he said he didn't do much post-processing, just some photo software, this Affinity, and anti-noise software. So I could look into those, what those are too. I mean, I'm just amazed. I'm not sure how long he actually exposed, but it must have been all night long to get that. What are these not good for, these robot telescopes? How about there's Neptune. You see it? That's that one pixel right there. So it's not good for small things. The moon, not too bad. Even the sun, a little bit bigger. I've taken, which I could show later. I can see sunspots with solar filters on the Dwarf too. So for big things, it's great. I was set up for the scouts there, daytime, look at the sun. They're like, this is neat, it's live, yeah. And can't quite see prominence, but it's a white light filter, not bad. But the details in there, even like on the moon, I sort of semi-disagree. I took shots earlier this week before the rains came, when it was clear. And I got the moon, and there's also a sharpness feature in it, so I can sharpen up the image. So I get some pretty crisp images of the moon, which I thought were pretty neat. But sometimes they look a little fake, a little dithering around the outside too. So it's kind of a playoff, the actual imagery versus the digital enhancements. All depends on your flavor. And then if you know post-processing, probably smooth all out anyhow and play all sorts of nice games. Stefan's Quartet, where is it? Is it here? No, it's right in here. And that's with, like I said, 200 millimeter. With this guy on the table here, it'd be half that size, be even smaller. It wouldn't be hard to see. So that's disadvantage, so smaller stuff. But like I said, the ZWO one that's coming will be 250 millimeters, so it should be a little bit bigger in here, so that should be nice. And then, for instance, this guy, his club, he said, here's what I did with the Vespera, the 200 millimeter scope. And here's a buddy of his with a real rig with real imaging processing software. And you can see much more detail. So you can see that there is differences. But he set up all night and did this. And he set up, within, 15 minutes and did that. So it's a trade-off. So for the people who just want to get involved real quick and dirty, it's reasonable, I would think. Conclusions. The good. Well, fun for larger showcase targets. Like I said, it's the wide field view. Easy imaging. You can see a JPEG or TIFF right away on your tablet, which is kind of cool. And I said they had mosaic features, which the Dwarf 2 as well has. I'm not sure. I think they're going to put that in the SeeStar 50 as well, with some dithering, I think is a rumor. So that could be really good. So these are the things. This is why it's not out yet. They're still tweaking the software. And they will even after they deliver the scopes. The bad, well, they don't work for small targets, like I just said. They're not modular. Can't reuse equipment. I can do better with high-end equipment, as we saw. And of course, they're new companies. Will they last? I truly believe the ZWO's SeeStar 50 will last because ZWO ain't going anywhere, and they have a huge following for the professional field, right, and the semi-professionals, and lots of equipment out there. So, will a Kickstarter company for a Dwarf 2 last? I don't know. They seem to be so far so good, but they're only less than a year old, right? So, and the other guys, we'll have to see, like the Vespera's Fiona and the other one. We'll see if those guys survive too. But certainly I do believe there's interest because after I was looking at my videos, I said, oh my God, here's all our favorite YouTubers who are into astronomy, backyard astronomy, and everything else. And they're all reviewing these things, and so it's out there. And as the public learns, it'll give easier access, I think, to dabbling into astrophotography. I think this would be good for maybe everybody. So that's, I think, yep, that's all I got. So thank you. I don't care, sure.
Do we have any questions in the audience? All right, I'm going to bring the mic to you so the live stream can hear you. Oh, just so the live stream, people online can hear the question too.
Hey Keith, you mentioned that you said you took 15-second shots with that. So you said it tracks or it doesn't track?
Testing. Oh, I'm on now. It does track. You can go from a fraction of a second to take pictures of the moon and stuff like that up to 15 seconds max. And it's got a gain which goes 1 to 200, I think. There's the IR cut filter on and off. And it's got like sharpness, hue, and brightness. I haven't even tried those yet, but it up to 15 per image, per snapshot.
Roughly how big are the files when you're done?
I don't know. I have not looked yet.
Oh, okay.
I mean, talk about a moron like myself who's not really doing astrophotography. I'm more a visual guy. Here's the Dwarf 2 app on the big tablet. Can you see that? Maybe? Is your AI following, or should I walk in front of the...
I should be following.
I don't know. It's not...
It's checking you. Yep.
So, and it's like, well, I don't know where the instructions are. I'm lazy. I'm just going to goof around. That's what I did the whole time. Where are the instructions? Oh, it's right here called tutorials. I should hit that button right there. Duh, there's the website. So, and then if you go back to the app again, so it's basically easy. And then it's albums. You hit the album button, and it goes into the, I can show pictures, actually. It talks to the scope, which is on, and I'll show pictures. Here's ones of the moon I had and stuff like that. Too bad we can't project them bigger. But there's the moon. It's fighting me, but it's not too bad. I mean, it's kind of exaggerated. It's through clouds and stuff. That's the nice thing about this, too, because the other night it was cloudy, Monday night or whatever, and there's clouds and stuff, and there's the moon out, and well, I adjusted the settings, and the moon looks pretty sharp. So, digital imagery does have its advantages. And so basically, like I said, I got a bunch of images here, a whole bunch of the moon there. I had some of the, here's what it looked like before. I said it was very cloudy out that night. You can see the haze around the moon and stuff. And from that, I went to the other picture you saw. Let's see. I had pictures somewhere of the sun. It's got a download. You can actually download to the device as well. So I have pictures on my phone, not to this device. And I think only one device at a time can really talk to it, which is probably a safe thing. But yeah, I had some pictures of Pleiades and stuff like that. But here's is this 31? Yeah, quick and dirty, without any processing. You see a lot of noise. Here's 31, 32, and 110 over there. I had some nice pictures of North American Nebula when I first played this game in the dark. But as I learned to post-process with processing software, a lot of stuff will go away. I'll be able to reduce the stars. I took no darks, so that noise is not extracted out at all. So I need to take those, and that way I'll have a library we can go against, right, to subtract stuff out when there's the on-screen stacking. And these are just the JPEGs. The actual files, I don't know. I mean, I think it's a 4K sensor, which the other ones will be only 1K sensors, 1024, or 1080 rather. Matter here's a movie of you. I don't. It can't stream fast enough, but I have a picture of you as one of the thumbnails here. But we took some daytime pictures. Here's some pictures of the. That's a movie, darn. Here's a picture of the sun with clouds and stuff like that. And then I figured how to dim it down. I actually got the sun here, and if you zoom in, there's some sunspots, like a white light filter. You can see the sunspots maybe on the, So, but I mean, just to go out there and sit up, and within 3 minutes, I got like, yeah, look at this. Oh, that's cool. So for the scouts, it worked out really well in the merit badge classes. I'd go up there for a day or so, and here's a picture of my face. I don't know. Take snapshots. Yeah, that was a zoomed in lens. I was goofing around when we were out there at Cherry Springs. So somewhere I had. Ooh, is this? That's not the Trifid. That must be the M8, right? So stars are bloated. I can learn how to focus too. It has issues, but it does autofocus. But you can also, zoom in and touch plus and minus on focus as well. So for wide field stuff, it's it's something. And the advantage is I didn't spend a lot, and I want to see if I'm going to dabble in astrophotography. What a cheap way to get into this. I'm sure a lot of people are going to play that game, So, but it's different. It's neat, and it's low cost of entry. So, like I said, I just fear that in the future, hopefully, we just have to sign up for Cherry Springs early before most other people do, because our club, we tend to go to Cherry Springs, and like 10 of us or 15 of us will go out there, and we try at least. I missed Cherry Springs officially, but I got into Black Forest because I signed up early enough. Cherry Springs sold out within 2 days, and that night where we were at Black Forest, my brother didn't make it either, so he had to park on the side and walk in. He said on the public side there must have been 1,000 people, and we have 500 people on the semi-professional side, so there's 1,500 people there that night. And of course, we're trying to take pictures and stuff, and unfortunately, someone got excited and we saw some fireworks on the side. Like, what are these fireworks doing? So, unfortunately, I think Cherry Springs is getting a little crazy. We'll hopefully have more control. Here's a quickie of the North American nebula. You can sort of see the hook there, right? That's Mexico, and there's Florida. Sort of quick and dirty, And that was just my little tripod on this thing on top of my car. I'm inside my car doing other ham radio stuff for about an hour. I was just taking pictures. And I said, I better go to my sunroof, bring it in. So that's the advantage of these smaller devices. So any other questions, or are we utterly impressed? I'm going to go out and buy one now. And I don't work for these companies, by the way. just kind of cool.
Let me just quickly check the live stream chat to see if there's anything there, and then let's see.
Is anyone out there?
Mike Blake is just thanking you for the talk. So
thank you much.
Otherwise, no questions from the chat, so we're all set.
Nifty.
All right, so we'll take a brief break while we get the Zoom session started for our next presentation, which I believe is the one we added, the Cherry Springs. Yes.
Yep. Very cool.
So Susan Schenk is one of the rangers from Cherry Springs, and he'll be talking over Zoom. So we just got to get it set up on here and connected with her. So just bear with us for that, and we'll get started in the next few minutes. right, good afternoon, everyone. We're ready for our next presentation, this one on Cherry Springs State Park, which was actually brought up in our last talk a couple times with Keith and with the electronic assisted astronomy. And today we have Susan Schenk, who's an environmental education specialist. So I will pass it off to you, Susan.
Hi, everyone. Yes, my name is Susan, and I lead and develop all of the environmental education programs here at Cherry Springs State Park. And this afternoon, I wanted to go over with you visiting Cherry Springs State Park as an astronomer or an astrophotographer, rather than just visiting as a member of the general public that may not be bringing quite the level of equipment and wanting the same kind of environment. So we're going to go over what it's like visiting Cherry Springs as an astronomer, and then we'll have some time at the end as well to go over any questions you guys might have that you've always wanted to, in more or less in person, ask of someone familiar with Cherry Springs State Park. So at Cherry Springs, like all of Pennsylvania state parks, we provide opportunities for healthful outdoor recreation and service classrooms for environmental education. And Cherry Springs is a great embodiment of that. We've got astronomers, astrophotographers, all you folks out on the overnight field with equipment. And it's a type of recreation. You know, it may not be the same as cross-country skiing or hiking or what have you, but you're still enjoying yourself outside and doing what you enjoy. And we also do a ton of public programs in a different section of the park. So for those of you not familiar with Cherry Springs, just as a really speedy review, where's Cherry Springs? There we are in north central Pennsylvania, just to the south and west of where you are now at Kopernik. And here is another image of Commonwealth of Pennsylvania, and then with the dark spots being the darkest sites in our state. So step one in visiting Cherry Springs is know where you're going. There are a couple different sections to the park, and I want to make sure that when you're visiting that you're choosing the spot that best lines up with what you wanted to do that evening. All right, so the first step is arrive in the daylight. Partially because if you're on the overnight field, if you're on the field that we've set aside, especially for people bringing technical equipment, whether that's imaging equipment, observing equipment, a combination of the two, when you're bringing all of that, know where you're going, because there's a gate that crosses that area of the park, and you won't be able to get in after dark. So Cherry Springs here is embedded in an area of Pennsylvania called the Pennsylvania Wilds. We're surrounded by several different state parks, and you can get there if you're arriving from the north, which I'm imagining many of you are, but since this is also being streamed on YouTube, maybe you're visiting from somewhere else here. So we have a map put out by the Potter-Tioga Visitors Bureau. It's got the roads that most people want to drive on. There are other roads, but they're not as well maintained. So I recommend either routes 44, 6, 144, 449 coming in from the north as well. So let's go over the two sections of Cherry Springs. We have highlighted here in green, in a green polygon, is the overnight astronomy observation field, which is that field that I mentioned where it is set aside specifically for people bringing technical observing or imaging equipment. And then we also have the night sky public viewing area. And that is more for members of the general public who are stopping by, may or may not be bringing technical equipment, but they're not staying the night. And there's fewer restrictions on that side of the field and in that part of the park. So this is just again to highlight that the overnight astronomy observation field is best if you want to do serious observing and imaging at Cherry Springs. So this is how you recognize you're on the overnight astronomy observation field. It has multiple telescope domes. We'll get into those domes in a little bit. For those of you familiar with Cherry Springs, you already know the story behind all that, but in a little bit I'll get into that for folks that aren't quite as familiar. So it is best for astronomers and astrophotographers with technical equipment. So there's strict regulations. So no white light allowed at all. So that does include dome lights in cars, reverse lights, headlights in cars. None of that is allowed on the overnight field. And as I mentioned before, there is a gate that goes across the entrance to the field that prevents people from leaving and from entering. So you don't have to deal with headlight spill from people directly entering or directly leaving the astronomy observation field. If you are a seasoned camper, but maybe you haven't combined camping and astronomy, just note that we don't allow campfires on this portion of the park. As you can imagine, smoke and fire are not great combinations with technical equipment. So you will, sandwiches are great. You'll have to figure out other ways to cook your dinner. As far as fees go, there is a $15 overnight fee each time you stay on the overnight field. And we'll go over the couple of different options for paying that in a little bit. And just for your own peace of mind, we ask the public to stay off the overnight astronomy observation field if they don't have equipment. If you're visiting Cherry Springs and you run into any problems, please contact us at the park office, and we will work with you and help you get things sorted out. We generally don't run in. I don't want this to seem like we run into problems constantly, but just in case, it's always good to get in touch with us if you have any questions. So, how to pay for visiting the overnight astronomy observation field? There's two options. Your first option is great for if you visit often. We have something called the Galaxy Pass. And the Galaxy Pass is available January 1st, around January 1st of the calendar year. And it's $65, and it means that you can visit Cherry Springs as much as you want. You still have to fill out an envelope with your information. That way we know how much each pass is being used. But you don't have to pay every single time. It's just a one-time payment of $65. If you're thinking, well, gosh, I'm not going to come up there that much. We also have honor envelopes where you fill out this envelope. This is a representation of an honor envelope. This is not an exact replica of the honor envelopes that we use, but they're very similar. Fill out your information, put $15. I recommend bringing cash or increments of 15 if you're staying multiple nights in that envelope. Fill it out and stick it in the collection tube. What do we provide for you on that overnight field? We've got electric pedestals with both 30 amp and 50 amp service. There are also flush restrooms, only available during the warmer months from mid-April through the end of October, so they will be shutting down here on October 28th is when we shut off our potable water, we shut off the flush restrooms. Do note that if you're visiting later in the season or very early in the season, we do provide a vault toilet, a pit toilet near the back of the field that is open all year round. And I mentioned it, but didn't directly speak to it. During the warmer seasons, we also have potable water available on this field too. So the only thing that we don't have on this field is showers. Luckily, you can go down to Lyman Run State Park. It's a 15 or 20 minute drive, relatively close, and you can take a shower there. They're $4 a person, and that fee is for anyone not camping directly at Lyman Run. So yes, even though Cherry Springs is a state park and is affiliated in some regards with Lyman Run, we just ask that folks not staying directly at Lyman Run do pay that $4 fee. And you can do that with cash in an envelope at the shower, or swing by the park office and we can process cards if you're not the kind of person to carry cash. We do have grocery stores nearby. And if you go north, you'll end up in Coudersport at their Save-A-Lot Foods. And if you go southeast, you'll end up in Gailton at their grocery store. And they have the basics, but they're not going to have a lot of international foods. So just keep that in mind as you're planning meals. First, if you need to run into town and grab some groceries, just keep in mind that our grocery stores here have a lot of basic food, but they don't have sort of anything super trendy. So what's in those telescope domes? Nothing. Nothing's in there. They are vintage domes, and they have fallen into a bit of disrepair, and so we aren't able to use them at this time. In the future, potentially, I can't really speak to if there's any timeline with reopening them, but it's not like at Kopernik where there's telescopes installed in the domes and that you are able to use them. There's nothing in there but birds' nests and grass. So that's what those domes are all about. Let's get into, just very briefly, the night sky public viewing area, because you might have family members that maybe don't want to, I don't want to stay overnight on the astronomy field, but I want to come for a little bit and stargaze. Where can I go? Is there a place for me at Cherry Springs? Definitely. There is the night sky public viewing area, and honestly, it is the best fit for most public visitors. People coming for a short time to see the night sky. And this is what the entrance to the night sky public viewing area looks like. You'll notice it has a single telescope dome, also decommissioned, there to sort of indicate that there's only one dome, and this is where you go if you're just wanting to see and admire Cherry Springs' dark skies. This is where we do public programs as well. So if you are hoping to attend a public program, if you are looking to volunteer with public programs, get in touch with me afterwards, and we can talk about that. We're always looking for help and volunteers. But if you're looking to do serious imaging, observing, I would recommend the overnight field just because it does come with more white light restrictions, headlight restrictions, and you won't run into as many light spill situations as you will over here on this field. So as winter approaches, you may be thinking, oh, right, all right, winter skies are clear skies. Let's do this. Keep in mind, upstate New York and north central Pennsylvania are very close ecologically, and winter looks like this. So it might be icy, it might be snowy, and we do not plow up at Cherry Springs. We plow a small portion, enough to turn around, but not enough to park a camper, not enough to set up, for the very bold and brave, a tent, not enough to car camp. That is on the overnight field. We don't maintain it that way in the winter. So keep that in mind if you have a really rugged vehicle and you want to bring it up to the overnight astronomers' observation area and camp out overnight, observe, image. Please do so. Just know that the roads will be pretty lightly maintained and know what you're getting into. So we all know that, as astronomers and astrophotographers, you guys have a lot of fun at night. During the day, there's also a bunch of stuff to do around. You can go to Lyman Run State Park. There's a free beach. You can rent boats. You can also stop by the Pennsylvania Lumber Museum. They have trains and lumber camps set up, and during certain times of year, they do little reenactments, and they run a sawmill, and I think it's fascinating, especially if you're into history. I highly recommend going to the Lumber Museum. You can go to the Pennsylvania Grand Canyon, rent bikes, go on a covered wagon tour if you're feeling a little bit touristy. And if you are you're thinking that I've kind of missed the mark and that's not really what you're into, visit pottertioga.com. They will give you some more ideas about what you can do to, while you're waiting for the sky to get dark, if it's not sleeping. So other things to keep in mind, please use red and dim light. Red and dim light. I know for some of you this is, of course, I use dim red light. But that's something that you may not consider if you're used to being out at night by yourself. Headlamps can point directly in people's eyes. So like this gentleman in the photo, he's doing things with his camera. That's shining on his camera, but if he's going to turn and look to someone speaking, he's going to shine that bright light right in their eyes. Doesn't mean to, but it can be a point of contention. So just keep that in mind. Oh, I went backwards. One moment. I really recommend a variable red light. They, handheld, you can make them dim, you can make them bright. Some of them you can even switch to white, but don't do that, but you can. And it's $16 on Amazon, so if you don't already have one, it's a great tool to add to your toolkit if you are looking for something that's dimmable and will not, be a big beam on your head that's going to shine accidentally in somebody's eyes. Also, bring layers. Cherry Springs is like Kopernik. It is up on top of a hill, it's exposed, and it gets cold. And it's also damper than you would expect. The dew really seems to settle in pretty thickly. So if you have dew heaters and other kinds of moisture prevention setups within your equipment, please be sure to bring those along, because you want to make sure you're having the most successful night you can. And this is just sort of a graphic here showing, August, for example. If you were to come in August, well, sure, it's warm parts of the day. Other parts of the day are, could be 55 degrees, which if you're used to 85 and sunny can seem pretty chilly. All right. Also, bring something comfy to sit on. I know that as astronomers, everybody has, their own setup of what they find comfortable. Just remember your comfy seats. All right. If you are more of a, oh no, I want real time. Show me what Cherry Springs State Park looks like right now. This is not Cherry Springs State Park this immediate moment. However, if you would like to see Cherry Springs, our Dark Sky Fund has set up this webcam, and you can go see the current conditions. Granted, these are this is in the night sky public viewing area. This isn't the exact geographical location of the overnight field, but it's very close. It's close enough that you get a very good general idea of what the skies are doing. All right, just please keep in mind, I'm not sure what the regulations are at New York state parks. Just know at Pennsylvania state parks, please no alcohol or recreational drugs. Please also don't bring your pet. It can be sort of overwhelming for a pet to be in a dark area near people that they don't know and crashing into technical equipment. I know, and also I know your dog is perfectly well behaved, and unfortunately not everyone's dog is. Of course, if you do have a trained service animal, please bring them with you. They're always welcome. Also, lasers. So a note about lasers is while you're at Cherry Springs imaging and observing, you may see lasers. That's me. That's me over on the night sky public viewing area, or that is our other educator, Steve, or one of our trained volunteers. So if you're the kind of person that likes to use a laser to point out stuff in the sky when you do outreach on your own, please don't bring that to Cherry Springs. Your fellow astronomers will thank you, and our staff will thank you as well. So what if your family wants a tour and you don't necessarily want to be the one to give it? We have free tours on Friday, Saturday, and some Sunday nights from mid-May to mid-October. And we invite everybody to attend. Even if, as an astronomer or an imager, you're just, I'm not feeling it tonight. Let's I don't know, let's go on a tour. Please come. We'd love to have you. You don't have to register, but you could. We do provide information on whether we're, canceling due to clouds and what have you through our direct registration. You can get the tour times and events on our events calendar. We do also offer private tours if folks in your family or yourself are interested in that. We partner with North Star Outdoor Guides. Their tours are limited to 16 people each, and it's $25 a person. Also, you can find those tours on that same events calendar. And so, hang on one second. I wanted to back up slightly and just talk about lasers and other possible sources of annoyance for people who, you're trying to observe, you're trying to capture an image. If you want to be guaranteed absolutely no lasers, like nothing like that at all, I would recommend coming Monday through Thursday. That we don't typically do unless there's some major astronomical events. We don't typically do public programs on Monday, Tuesday, Wednesday, or Thursday nights. So if you need to capture an image that is, as obstruction-free as possible from lasers or foot traffic or anything like that, I recommend coming during the week, just so you have a bit more of a private experience. And with that, does anyone out there have questions or comments about visiting Cherry Springs? I'm happy to answer them if you have any.
Yep,
I see a hand. I see your hand.
Thank you. Is this okay?
Yes, I can hear you.
So I have a small camper van, and I'm not interested in the fancy part, but I'd like to come up and park in the public park at night for a couple of hours. Is that permissible?
Yes, that is permissible, as long as you don't camp overnight in your camper van in the parking lot. If you wanted to camp overnight, we do have a campground you can get a site at the very near the the public viewing field as well. I don't recommend observing from your vehicle in the visitor parking lot because of headlights. They come in and your night vision's always readjusting. I recommend parking and then walking out onto the field with a lawn chair or blanket or what have you.
Thank you.
Any other questions from the audience? No? Let me quickly check the live chat here, see if anything came through there. Doesn't look like it at this time. So yeah, if there's no other questions out here, thank you so much, Susan. Let me make sure I'm in frame here. I've been to Cherry Springs a couple times myself, and it's just been extraordinary every time. So it was great to have some more information about it. And
well, great.
Yeah,
it's been great talking with all of you. Enjoyed the presentation last night as well. Sorry I couldn't make it up there in person today, but happy stargazing, everybody, and until next time.
all right. Thank you, Susan. Not that one. There we go. All right, so yeah, our next presentation is going to be at 4 p.m. on the upcoming solar eclipses, and that's hosted by Zoe Lerner-Ponterio. She'll be presenting. She's from the Spacecraft Planetary Imaging Facility. So we've got a little bit of time so you can take about a half-hour break or so, and we'll get started right at 4 p.m. back, everyone, for our next presentation. So we've done 3 or 4 presentations now today, and we have Zoe Lerner-Ponterio from the Spacecraft Planetary Image Facility at Cornell University. She's given a number of presentations now here at Kopernik Observatory, so we're so thankful to have you back. And today we're talking solar eclipses, both the science of eclipses and the 2 upcoming eclipses on the horizon, one next week. So without further ado, I'll pass it off to you, Zoe.
All right, thank you very much. I'm excited to be back at Kopernik again. Hopefully it's going to clear up a bit here, and we'll have some viewing in the evening. But yes, I was asked a few years ago to put together a talk on eclipses for a lunar eclipse that was happening. And in true fashion, I suddenly realized the morning of that I had not made the talk. And I decided, well, I guess I have to throw something together pretty fast. So I do like to tell the story of how this talk came to be, which was me furiously just coming up with like, okay, I want to say this about eclipses, go find a picture that says that, throw that into a file, and just kind of did that. And what happens, of course, though, since I do presentations and I'm a teacher, is that I inevitably ask myself questions. So I'll make a statement in my head about something, and then I will hear the audience member in my head, the child, ask that question, and then I was like, well, I better have an answer for that. And so I just continued to say things, ask questions, answer, and throw image after image into a file. And what came out of it in a span of a furious 2 hours was this talk, which ended up taking a journey that I did not know it was going to take when I started out. And so now you get to kind of go on this journey with me of what happens when you ask me to, oh, just do a basic talk on eclipses. And so before we get started, we need to make sure that we acknowledge the fact that in its essence, an eclipse is a shadow, right? We're about blocking the light of one thing with another thing, and then observing the effects of that. So we do want to make sure that we understand shadow basics. All right, so I'm going to use this diagram of a lunar eclipse because it's a little easier to see what's going on here. If you were to be floating in space, say at this position, and if you looked in this direction, you would be able to see the sun. If you looked in this direction, you'd be looking at right, you'd just barely be able to see the sun, and if you turned your gaze a little bit, you would not be able to see the sun. The Earth would be blocking it. And so this is a region that we call the penumbra. The word umbra, of course, is from Latin for shadow. If you speak French, you know that the French word for shadow is l'ombre, same derivative. So this is the penumbra, but if you were floating, say, here, any direction you try to look, you cannot see the sun. The Earth is completely obscuring your view of it, and that is what we call the umbra. So that's like full-on shadow, whereas the other one is more partial shadow. And so a lunar eclipse will happen when the moon passes into the Earth's shadow, which is, from the point of view of being on Earth, a fundamentally different phenomenon than that of a solar eclipse, where the moon is casting a shadow upon the Earth. And so we are going to talk about both of these today to understand that even though they are a similar alignment of objects, the fact that we are here on Earth means that these are 2 very different things from our perspective. So we're going to talk about solar eclipses first. And so here's a diagram of you're standing on the ground. Obviously, everything is very exaggerated here. But we have this point of view of if you were here on the ground, that's an umbra, and you would be getting a total solar eclipse. The moon completely blocks the sun from your view. But if you were standing here at C in the penumbra, that would be a partial eclipse that you saw. So that's basically the explanation for why some people would see a total and some would see a partial. It has to do with where you are in reference to where the moon's shadow is. Now, of course, we live in an age when we send spacecraft into space to take beautiful images. And so instead of simply having the perspective of seeing this from the ground, we actually can watch it happen in space. And this was a movie that I'm going to show you from the 2017 total solar eclipse that crossed across the United States. So if you watch very carefully, right up here, the United States is right here, so we want to pay close attention. There it is. From 1,000,000 miles away, there was the shadow of the moon passing across the Earth, with the United States being the main target. So you can see that a lot of things affect who can see this. The Earth is spinning, the Earth is round, the moon is orbiting, and the Earth is moving around the sun. A lot of things are moving and round, and this means it's a fleeting little blip. And if you were lucky enough to be in that umbra, that path of totality, you get treated to what I am told at least is one of the most spectacular natural phenomenon you can see. I have actually never seen one, so really crossing my fingers for my chance in a few months. What you see here is the moon completely blocking what we call the surface of the sun. Now you might say, well, the sun is not a solid object, how can it have a surface? We actually do define the surface of the sun as the place where all the light is coming from. There is a place where below that, the light that's coming from that part of the sun is actually blocked from us. It's called the photosphere. It's this layer where all the light that manages to escape the sun and make it to Earth is actually coming from. And that is entirely blocked in a total solar eclipse. So the only thing you can see of the sun are those solar prominences, those balls of plasma that are erupting and falling back down, and the sun's atmosphere, which we call the corona. Now, this has an interesting historical fact because we've known and been able to predict eclipses for centuries. So this is not something that has been mysterious to people of ancient times at all. But one of the interesting things that happened with Einstein was that his prediction that gravity warped space-time, this idea of it actually curves space. One way they figured out that they could test it was by looking at the object with the biggest gravity that we have close by, the sun, and seeing if the sun bends space around it. Now, of course, it's very hard to see this normally because the sun is very bright, but during a total solar eclipse, you can suddenly then see stars. And they used telescopes to look at stars that were very close to the surface of the sun. And sure enough, they saw stars they shouldn't have been able to see. They saw stars that in actuality were behind the sun, and yet their light was being bent through curved space around the sun and showing up in our view. And that was one of the really big, solid, anybody can see this and observe this pieces of evidence that Einstein was on the right track with his ideas. So total solar eclipses, super cool, but they're actually not the only type of eclipse. Let's appreciate the beauty of the fact that the moon is just at the right size to just cover that sun. That the moon and the sun are approximately the same size in our sky, from a quirk of the moon being 1,000 times smaller but 1,000 times closer. And the moon has not always been at the distance it is today. The moon started out much closer to Earth, and the Earth's day was much shorter. So if you went back a couple billion years, you had a 17-hour day and a very big moon in your sky. But the moon is drifting away from us. Currently, it's drifting away at about the width of your thumb every year. So nothing we need to really worry about. But it does mean that the moon is getting smaller in our sky. Now, also as the moon goes around the Earth, it's not a perfect circle. And that, who's heard of a supermoon? Who sees this in the headlines? Like, we never talked about this 10 years ago, but suddenly now everyone's like, oh my gosh, the supermoon. Guess what? They happen twice a year. It's not a big deal. But the moon is basically in an oblong orbit, very slightly, but that means that it sometimes does look a little bigger or smaller in the sky. And a supermoon is basically just a point where the moon's at its closest to us and also happens to be at the full moon phase at the same time. I really can't tell the difference, I'll be honest. I look up, I'm like, looks the same size. It's a slight difference. But if you're just covering the sun with your disk, it might make a difference. Because if you move, exaggerated in this diagram, if you move the moon farther away, the length of that umbra is such that suddenly that umbra narrows and doesn't make it to the surface. and instead forms a thing we call the antumbra. So what in the world is that? So you might have noticed before we had A and we had C, and you might have wondered where's B. Well, A is the total, B is the partial, but if you happen to find yourself in that antumbra, you see what we call an annular eclipse. We can all now experience this if we want to just do a quick little activity. I do this with kids, but we can all do it, provided you're the kind of person that can, in fact, close one eye. If you can't, you can go home after this and enlist a family or friend to cover one of your eyes for you and try this. But basically, I want you to have your fist at one hand and your thumb up on your other. All right, now, if you close one eye still, it's clear that your fist is bigger than your thumb. Duh. But if you start to move your thumb closer to that open eye, it starts to look bigger and bigger until you can find that distance where you can actually cover your whole fist with your thumb. But now move that thumb a little farther away from you and notice that you can make out a bit of your fist behind the thumb, around the edge of the thumb. Move the thumb closer. Oh, no, blocking the whole fist again. You can play this game all you want, but that's actually what's happening here. If the moon is near its farthest point from Earth, it's a little smaller in the sky, and it isn't quite big enough to cover the whole disk of the sun. And so you get this. This is amazing. I think of the fact that you see artistic representations of the moon having that shape, even though the moon never actually has that shape, but something does, so maybe this is where the inspiration came from. And if you find yourself in the path of annularity, you get treated to what's sometimes called the ring of fire, where you get the moon right lined up with the sun, but not big enough to block the whole disk. This is the type of eclipse that is happening a week from today. So unfortunately, you're not going to get treated to this show if you stick around here. It's going to be a partial eclipse, only 24% coverage, and the weather is not looking good. Sorry. But like I said, you're not going to be missing much. Like, that's the most dramatic it's going to look. But wish me luck. I am going on my very first eclipse chase. I am flying down to Texas, and the weather for Odessa, Texas, which is my planned destination, is looking very nice. In fact, despite the fact it's super hot there now, a front is moving through right as Saturday comes, and the high is supposed to be 68. It's beautiful. It's, so I'm going to be up very early Saturday, getting on the road. The eclipse starts there around 10:30 in the morning, peaks 1/4 to noon. So I'm hoping that I'm going to be able to see that ring of fire. Odessa is like right in the center there, so I'm hoping for a good show. So yeah, if you have last-minute plans to go travel, the path will go from Texas up through Oregon. You'll see a picture of it in a minute here. Now, one thing that people ask, therefore, is the concept that solar eclipses seem rare, right? And yet, if the moon is going around the Earth, it would seem that this should happen all the time, right? This alignment should happen every time the moon goes around. So why is it that we don't get a lunar eclipse every full moon and a solar eclipse every new moon? Why don't we get eclipses every single month? And the fact is that, in addition to not being a perfect circle, it's also tipped. The moon's orbit is tipped at 11 degrees compared to the Earth's orbit around the sun. And that means that most of the time, the umbra misses. It passes above. The Earth's umbra also misses the moon. So the umbras don't line up. Space is honestly a lot more empty than most people give it credit for. The moon is about 1/4 the width of the Earth. It's approximately the width of the continental United States. And if we would do the distances correctly, we have an Earth globe here, you could fit 30 Earths between the Earth and the moon. And then, as I said, the sun is approximately 1,000 times farther away than that. So you've got really tiny objects in a lot of empty space. It is really easy, actually, to miss. It is hard to get them to line up. But twice a year, as this moves around, you get that effect. You get an alignment here where what we call the nodes, the places where the two orbits intersect, do line up. And so that twice a year is known as eclipse season. And yes, you do get eclipses twice a year. So then why in the world does it still seem rare? Now you might say like, well, yeah, because lunar eclipses, they aren't so rare. To see a lunar eclipse is rather easy. They happen twice a year, and if you happen to be anywhere on the nighttime side of the Earth when it happens, everyone gets to see it, assuming you have clear weather. And so because of the fact that everyone on this side of the Earth gets to look up and see the moon pass through the Earth's shadow, which is plenty big to cover it, yes, it is easier for the average person to catch a lunar eclipse. Solar eclipses, though, we can see the moon has a much tinier shadow and only casts itself on one little part of the Earth. And let's keep in mind that the Earth is also mostly covered in water, and even the land of Earth is mostly covered in very sparsely populated land. And so when we look at the map of 20 years of solar eclipses, these are all the solar eclipses, total and annular, from 2021 to 2040, we see that, oh yeah, there's lots of them, but only a small little fraction of people will actually find themselves in the path and able to view it. A lot of them just happen over open ocean, or in the Arctic or Antarctic, or, you know, running through the outback in Australia. So this is why they seem rare. It's not that they're rare to occur, it's that they're rare to be observed. Now, of course, you might be noticing something about this, and that is the two very notable crossings. This red one, the red ones are all annular eclipses. So this red one is the one a week from today. As I said, it's passing Texas all the way up through Oregon. But then of real interest to us, of course, is this blue one, which signifies not an annular but a total, because we are right here. And that will be April 8th of next year. It's here. And that is the path of totality. So down here where I live in Ithaca, no point in sticking around, right? It's going to be like 98, 99% coverage. So everyone I'm telling around me, I'm like, just drive north. So Syracuse will be just inside totality. Rochester, much closer to the center. Buffalo, right on the money. Now, why does it matter? Once you're in path of totality, why would you make an effort to get closer to the center? The length of totality. If you're right on the edge, that totality just clips and it will be very brief. But if you get closer toward the center, it lasts longer because you're more perfectly aligned. I will be up in Oswego, right around here, somewhere in here, and I will get 3.5 minutes up there of totality, whereas Syracuse will be under 2 minutes. So it does matter as far north as you can get. So please plan to drive north. Now you might say, okay, day of, weather's cloudy, it's dark, it's rainy, so I won't do it. No, still do it. Because when a total eclipse happens, it becomes like night. It doesn't matter how cloudy it is, you notice whether it's day or night. You will notice it happened. True, you won't get the coolness of being able to look up and see the sun's corona with your bare eyes, which you can do only during totality, but you will notice it get dark. The animals will react. The temperature will change. I am told this by people that have seen it. They said it is still totally worth going to be in totality, even if it's completely cloudy. So do that. So let's review again. Please only look at the sun with solar glasses. Do not buy them from Amazon. The AAS, the American Astronomical Society, has on their website a list of about 15 reputable sellers of total solar eclipse glasses. So please get yourself some of those glasses. As I said, the one time that you can take them off is during totality. You can take them off and look directly up at the sun. Otherwise, don't. And I do want to stress there's a procedure to it. You've got your glasses. The first step is looking down, put glasses on. Then look up at sun. Even with the glasses, don't look longer for like 20 or 30 seconds. And then, here's the key thing, look down and then take them off. Do not be like, okay. This is a common thing. So practice, seriously, the day before, make yourself practice doing this procedure. Get your habit. I don't want anyone's eyes to get hurt. Okay, Drew's got some examples right here with holes in them, I see.
Yes.
That won't help, Drew.
Well, actually, I specifically brought that out. Somebody brought this up to me a few years ago.
Mm-hmm.
And what they did was they put the solar glasses on, then they took the binoculars thinking they would get a much better view of it. And that's what happened to the
Oh my gosh.
glasses.
They burned a hole in them.
Fortunately for him, it just burned his cheeks a bit. He did not go blind.
Oh my gosh.
But don't do this.
Don't do that. Now, something I did purchase along with my glasses was a filter to place in front of a camera. So I'm going to try my hand at taking a picture of the one in a week. We'll see how it goes. Like I said, I'm not an eclipse chaser or a photographer, so what'll happen will happen. So that is kind of the conclusion of talking about solar eclipses from Earth. So I do want to stop and ask, like, what questions do people have? Where you are along the line, so let's go back. Yes, that only matters for timing. So anywhere near that red line, you're going to get the same amount of totality. But remember, that shadow is moving. Remember the movie. Like, it's moving and booking it quite steadily. So you'll want to look up the timing. There are plenty of
phone apps that will sense your location and tell you exactly when things are happening. There's even ones that will give you notifications, audio notifications, calling out when things are going to happen.
But so like Buffalo or Watertown, doesn't matter?
You'll get the same amount of totality. It's just a matter of timing.
Trying to find places to lodge already are crazy.
Exactly. I think I got the last Verbo along the lake, so sorry. If you haven't made your plans, you better have friends or family to go stay with, because I don't think there's a single hotel room or Verbo or Airbnb left that's reasonably priced. Yes.
Okay, the other line there, you get vitality anywhere within those two lines.
Right, so I'm not sure what this yellow line is about, if anyone knows what that's signifying.
But yeah.
But yeah, anywhere between the blue lines, and the red line shows you that point of maximum length of totality.
Okay, so at the very end, about how much would that be versus center?
It drops off, as I said, Syracuse, I think it's like 1.5 minutes. And this end right here is getting 3.5 minutes. So in totality, I think in the line, they're getting a little over 4 minutes. So like I said, any amount you can get yourself over that blue line is good. Please do plan ahead. If the 2017 eclipse taught us anything, eclipse fever is on the rise. I think with the advent of social media and more people being aware of it and having seen people filming it, freaking out to it, want to see it. I reserved my Verbo for the whole weekend. My plan is to go up on Friday and not even try to be on the roads that day. The timing of the eclipse, again, depends where you are along the red line, but it's generally in the early afternoon. I know a lot of schools in totality have decided to not have school that day. I really hope they all do that or do an after-school program, because literally some of them would be having totality while kids were like on the buses on their way home, which I'm like, that'd be so weird and scary and unfortunate. So I'm really hoping that schools all coordinate a way for kids to enjoy them. Yes.
Along those lines, don't expect you're going to get someplace in an hour and a half, because traffic is horrendous, and it's even worse after the eclipse. So staying the extra day is very good advice.
Yeah. So yeah, our plan is to go back that Monday, but we're not in any hurry. So yeah, be prepared for traffic that day. Do not just expect it to be a normal day of hopping on 81 and heading north. Yeah. All right. Cool. All right. Well, this is the part where I was like, well, after solar eclipses, I should talk about lunar eclipses.
And I know the talk said it was about solar eclipses, but, you know, it's still an eclipse, and let's talk about it. So let's now look at the difference. Again, we said this is not the moon casting a shadow on us. This is us casting a shadow on the moon. And again, as this shows, the Earth casts a plenty big shadow for the moon to make its way through. It's not like a just big enough like the solar eclipse. and if you've ever gotten to see one, which is far more likely than having seen a solar one as we've talked about, you will notice that at first you cannot see the penumbra. This is actually, the penumbra's over the moon, and since it's just kind of dimming the whole moon, you don't really notice it. It's not until that umbra really starts to come in that you start to notice it. And then a really curious thing happens, which is as the umbra reaches the whole moon, it suddenly turns red or brown or various colors. Each one is a slightly different color. So what's happening there is that reddish-brown color is here, but because there's still a bright sliver of the moon, it's washing it out to your eyes, and you only really start to notice the reddish color when you start to actually enter totality. So this is known as the blood moon, of course. And the question, of course, is where is it coming from? Why is there a shadow? Well, the difference between who is casting the shadow is that the moon has no atmosphere, but the Earth does. And so I found this really kind of cool animation that shows if you were standing on the moon and watching this happen, you'd get a total solar eclipse, and that red light just passes around, and that red light is the Earth's atmosphere. So if we'd like to watch it one more time, it's pretty cool. Someday we'll have astronauts on the moon that'll actually get to see this. And that's why it's in the talk, because it is a solar eclipse for someone. So here's kind of an enhanced view of that totality you get on the moon. The light from the sun is being completely blocked, but sunlight is passing through the atmosphere of the Earth, and it's red for the same reason that sunsets are red. It's passing through a lot of the atmosphere. The reason our sky is blue is something called Rayleigh scattering. Our atmosphere tends to scatter blue light more effectively than red, which means that the more atmosphere the sunlight has to go through, the more blue light has been scattered away from your line of sight, and you're more getting a redder light. And so that's the reason the blood moon happens. And that's the reason the color can be different, because it really depends. Just as every sunset is a little different, every lunar eclipse color will be a little different. Sometimes it'll be affected if there's been a recent volcano that's gone off, or if it's winter or summer. All of these things can affect the particular shade that the blood moon takes on. So I really am looking forward to someday being able to show you actual videos of astronauts on the moon filming a solar eclipse for them, which is a lunar eclipse for us. Yes? It's going to be a lot harder. The diamond ring effect, if you don't know, is in a moment right before or right after totality. Of course, the moon is not a perfectly smooth surface. There are mountains and craters on the moon, and sometimes you'll get just a little snippet of sun that makes its way like between two mountains. And so you see the corona, but you also see this one bright dot. It's called the diamond ring effect. I don't have a picture of one. It would be harder to get that here because the Earth is overall smoother. You got a lot of water on the Earth making it very smooth, and the atmosphere distorts things. So you're not going to get a really sharp diamond ring effect as you would with the airless body of the moon passing in front. Not impossible, but it's not going to be dramatic. And you'd have to get it to where, again, you actually had mountains. Let's remember, 75% of the Earth is covered in water, which is very smooth overall. And in fact, the entire Earth's surface, if you made the Earth the size of a billiard ball, would be smoother than a billiard ball, right? On a global scale, it's not that rough. So on the same scale, the moon is rougher, so you can get that diamond ring effect. Maybe more like a ruby ring effect, we call it that. I don't know, we've never seen one, so someday we'll get actual footage. Any other questions about lunar eclipses?
And you might notice that, like, we're only halfway through the talk. And I told you, like, I didn't know where this talk was going to go when I started it. So this reached the point, like, okay, I've talked about eclipses, but I started to really now think about that whole annular thing. And the whole thing about, like, well, how big things are in the sky and whether it gets totally covered or not totally covered. And I really started to ponder that and started thinking, wait, what about in other places? Like, I just talked about going to the moon to see a solar eclipse from the moon, which on Earth we call a lunar eclipse, and that made me shift my perspective. And I said, well, how big the sun looks in your sky depends on where you are. And so on Earth, there's
the sky, and if you want to scale photographs to that, if you went to Venus, it would look a little bigger in your sky. Now, that is not a realistic picture from the surface of Venus for a number of reasons. The surface of Venus is not bright orange. The sky is dark and yellow. You cannot see stars on the surface of Venus. But if you could, we can see the size of the sun would be bigger. Now, you never can see the sun from the surface of Venus, and Venus has no moons, so no, Venus doesn't get any. And unfortunately, even though the sun is really big and dramatic in Mercury's sky, Mercury also has no moons. So Mercury also doesn't get treated to any eclipses. But as we head in the other direction, Mars does have 2 moons, and the sun is a little smaller in its sky. Once we get out to Jupiter, the sun gets very small in the sky. Saturn, Uranus, Neptune, and by the time you're out at Pluto, it's basically just a really bright star in the night sky. I just saw a simulation of what like Betelgeuse will look like in the sky if it goes supernova, and based on what I know, that'll be way brighter than the sun is at Pluto. So a curious thing that happens, of course, is the smaller you make the sun in the sky, the easier it is to block it. So now my brain went to, well, what are solar eclipses like on other planets? Well, as I said, Mars does indeed have moons. And here comes Phobos. So this is an actual movie taken by a Mars rover of a solar eclipse on Mars, or at least the best we can do for solar eclipses on Mars. Phobos is potato-shaped, only about 30 miles across at its widest. So no, even though it's really close to Mars, it is nowhere near big enough to cover the whole sun. Phobos orbits Mars so closely that it goes around 3 times a sol. That's a Martian day. So it's booking it. I mean, compared to Earth's moon that takes 4 weeks to go around 3 times a day is pretty fast. So it's
kind of more
eclipse thing, and you're never going to get totality. And Mars's other moon, Deimos, is both smaller and farther away, so this is the best that Deimos can pull off, which is not terribly impressive. But yeah, flying potato is what we often think of when we see Phobos going by. So you can even see some sunspots there as it passes there. Okay, so Mars doesn't get total solar eclipses, unfortunately, but yes, it does sort of get eclipses, right? Kind of. Let's go to Jupiter. Wow, that's not a hole in Jupiter, that's a shadow on Jupiter. And it's a shadow being cast by one of Jupiter's large 4 moons. So if you were there on Jupiter, you would indeed be treated to a total solar eclipse because the moon would be plenty big in your sky to block the very much smaller sun in the sky. And so we even have movies. On Jupiter, this does happen every orbit because the moons are much closer to Jupiter relative in size than the moon is to Earth. So you basically get solar eclipses every single moon orbit, and there's 4 moons big enough to cause eclipses. So yeah, now one of the things you might notice though, if you're really paying attention, is that the shadow cast on Jupiter by its moons is really sharp, as opposed to the shadow cast on Earth by its moon, which is really quite fuzzy. And this is one of the points at which I looked at and went, why is that? I asked myself, I was like, somebody's going to notice this and somebody's going to ask, because if I was in the audience, I'd be that person. And so I went to go figure it out. Well, it's all about geometry. So if we take this as a reference on Earth, and you look at the fact that that blurriness is happening because of the penumbra. So look at the size of the umbra, and then the size of the penumbra around it is comparably large, and that produces a very fuzzy shadow. However, on Jupiter, you've got a sun that's smaller in your sky, and so the effect of that is that the penumbra shrinks and the umbra grows. And so the size of that fuzzy penumbra gets small compared to the size of the very black complete umbra. And so that is why the shadow looks so sharp on Jupiter. It's just about the geometry of the fact that the sun is smaller in Jupiter's sky. Saturn, yep, definitely gets eclipses. Plenty of moons on Saturn to cast shadows. So this is the point at which now I'm like, well, do we have photos of eclipses beyond this? Now my brain's just going like, okay, have we caught an eclipse on Uranus? Yes, we have. So this is taken from Earth. That is Uranus's moon Ariel casting a shadow on Uranus. It's not very dramatic, mostly just because sunlight is so faint at this point. This picture actually is probably taken a bit in the infrared, not the visible light. And so Uranus itself is giving off infrared, which is why it doesn't look completely black, because the moon is only blocking the visible light from the sun. It's doing nothing to block the heat that's coming off of Uranus's clouds. All right, well, what about Neptune? The answer is no. We've never caught a picture of an eclipse in Neptune, and that's because it's actually really hard. Neptune only has one moon of decent size that could cause an eclipse, and that is Triton. And it turns out that Triton's orbit is really inclined with respect to Neptune's orbit around the sun, so much more dramatic than Earth's is. This is partly because Triton did not start out as a moon of Neptune. It was captured. Triton was likely a dwarf planet in the Kuiper Belt. It's about the same size as Pluto. So it and Pluto were chilling, and then Neptune came too close and grabbed Triton. The inclined orbit is one piece of evidence. The really big one is that, as this shows, Triton rotates in the opposite direction and orbits in the opposite direction. So it couldn't have formed there with Neptune. It was grabbed and brought in. And so this means that, like with the Earth, you're only going to get eclipses when you line up those nodes. And Neptune's year is, help me out here, 100 and some years long. The exact number just, Uranus is 84. 165 years. So yeah, Neptune probably has eclipse season, but yeah, a Neptune year is a really long time. So no, we have not yet caught a solar eclipse on Neptune, but it should be possible. But here it truly will be rare. So basically every 80 so years, you might get an alignment that could produce a solar eclipse on Neptune. So this is kind of where I was like, okay, so that was a cool little thing to go off on, solar eclipses from other worlds. So who has questions about that? Yeah, some more hands go up.
If you were on one of Jupiter's moons, could you get a solar eclipse from another one of Jupiter's moons?
Ooh, I love this, like, questions like, I didn't even ask that question, so you just gave me a new question. My guess is that the moon's orbits, I think, are not very inclined, so I'm going to say you would get some kind of alignment that, yes, I don't know if I'd have to look up if they can cause total solar eclipses, but you definitely at least could get partials, maybe annulars, because, yeah, they should line up at some point. Their orbits are shorter than Earth's moon. So I'm going to say yes, but now we're going to have to go investigate after this, aren't we? Yeah. So that's my guess answer is yes, but I don't exactly know what kind you would see. There's a hand back over here.
On the images you showed from Jupiter, you showed the shadows, if those are the actual photos. Looked like it was moving almost in sync with the rotation of the planet.
So, yeah, let's go back to that. Where is my... Yeah, so if you watch it, it's, yeah, so on Earth, one of the things that I didn't mention is the fact that, let's look back, kind of touched on it, but if you're looking at the tracks of solar eclipses on Earth, one of the things that you notice is they look really funky, right? Why do they look like that? Well, again, one of the things is that this is a flat map, right? Let's acknowledge the fact that Greenland is not that big. Antarctica is not that big. This is a Mercator projection. It is highly distorted. Earth is a round object, and the Earth is spinning, and the moon is orbiting, and the Earth is going around the moon. So these are windy paths because of all of those factors. You're casting a shadow that's moving across a round spinning object, and yes, that causes it, when you then stationary and flatten it, it makes it look very, very strange. But in that video we saw of the Earth, like, okay, that looks like the shadow's moving nice and straight, but again, the surface is curved and it's spinning. So that's an interesting thing to point out about Jupiter, and it really is just all about the orbital periods of those. So let's see here. Jupiter rotates every 10 hours, and Io's orbit is on the order of like a week or so. But again, you're only getting that alignment for a few hours. So just another interesting quirk that, yeah, I guess the path of totality does not move very much. So I guess if we lived on Jupiter, if you had that perspective, they'd be even rarer because only right there on Jupiter would you get to see it. But yeah, I hadn't noticed that before, but yeah, you really don't get much of a path. Interesting. Yeah, exactly. So that would be the upside. Is if you happen to be there, the totality would last. Yeah, a few hours. That'd be cool. Awesome. All right, so we're all good.
We have another question from the live chat.
Yes.
It's kind of a thought experiment, I think, more than anything, but it says if we could cool the Earth by putting a disk between us and the moon, what is the optimal size and distance for that disk satellite?
Okay, so the idea of, I guess, putting a structure in space that would partially block sunlight from the Earth and therefore cool the Earth slightly, and I guess is a solution to possibly climate change. I have heard something like this being proposed. It really would depend on just how much light you wanted to block. Let's keep in mind that the farther away you put that object, the smaller it will appear in our sky, and therefore the less sun it's going to block. Is it, it's possible to do that. I can think that there's probably cheaper and more efficient ways to try and keep the Earth from getting hotter, but it would work. There is a point. Does anyone in here know about Lagrangian points? No. All right. So you've heard of them. Okay. I did my math thesis on them. So they're basically points in a two-body system. So in this case, the sun and the Earth are your two bodies. Turns out you can solve that system exactly, but if you try and add a third body, it all falls apart, and we haven't mathematically solved the three-body problem. So what you do in these cases is you just assume that the mass of that third body is so small that it doesn't affect the system. And when you then calculate everything, you come up with 5 points of stability, where the gravitational pulls of those two objects are balanced enough that you have an equilibrium. Now, some of those are what we call unstable equilibria, which means it's like being at the top of the hill. Yeah, if you're right exactly balanced, you'll stay there, but any nudge and you'll drift away from that point. JWST orbits at one of the stable Lagrange points. So JWST does not orbit Earth like Hubble does. It actually orbits, get this, an empty point in space that is fixed with respect to the Earth and the sun. And so it's kind of like if you imagined you had a bowl, and instead of the object being down at the bottom of the bowl, you spun it so that it was rolling around inside the bowl. And JWST basically just does that and manages to use thrusters and stuff to maintain itself going at the right speed, that it never falls further into it. It just sits there and goes around an empty point in space, which is just really cool. So there are points in space where, yes, you could position something to just stably stay there, and they just happen to be at points where things tend to line up. So theoretically possible, and again, how big the structure is and how far away it is would depend on how much of the sun you would block. I mean, people have taken pictures of the ISS crossing across the sun and blocking it. So technically we already do that, I guess. But yeah. I've heard this proposed as an idea for combating global warming. I think there's better ones, but sure. We could do that. Any other questions? Because guess what? My brain didn't stop here. Of course it didn't. It kept going, because then I started like thinking about Mars's eclipses, and I started to question, like, is it though? Can we really call that an eclipse when it's not even covering most of the sun? So this then begged my question of like, well, what defines an eclipse? Because there is something else that looks a little more like this, and that's something that's called a transit. And if you look very carefully, this is a transit of Mercury. There's Mercury passing between us and the sun and blocking it slightly. So that was actually a cool thought experiment building into the next little line of thought that I went down. And so looking at that picture of an eclipse on Mars, I was like, well, that looks more like a transit to me. And so I asked the question, like, well, where's the division? Like, when does it transition from transit to eclipse? And guess what? No clear answer. An eclipse technically has to be the ability, apparently, to potentially cover the whole sun, which means that technically these are not eclipses under that definition. Another definition of eclipse is that it is specifically a phenomenon that occurs when a moon is blocking a star's light from the planet, or vice versa. That is specifically a moon issue, in which case this would be an eclipse. So there is actually no clear answer to this question. But yeah, you can get what's called transits, where the planets that are interior to your orbit, in our case Mercury and Venus, can pass between us and the sun. Again, this doesn't happen all the time because the orbits are not perfectly lined up, but every once in a while they do. This one happened in November of 2019. I was lucky enough to just happen to be down visiting the National Mall with my family that day, and so I got to see this through a telescope at the Smithsonian Air and Space Museum. It was very cool, and that's indeed what it looked like. It's just like this tiny little dot. A few years before that, the next one will be in 2032, if you'd like to mark your calendars, the next Mercury transit, 2032. Venus, of course, being bigger than Mercury, blocks more of the sun. It appears bigger in the sky and can block a larger dot, and there's a plain photobombing. So yet another example of, yes, we can put objects between us and the sun and block some of the sunlight. This one's not even in space. All right, so this one occurred in 2012. I also just managed to catch this one with my then very young sister-in-law, and I kind of dragged her out, and we were in Cortland, and we set up my telescope, and we caught it just as the sun was going down below the hills. So I just barely caught this one, and boy, am I glad I did, because the next one won't be till 2117. So sorry if you didn't see it in 2012. So yeah, planets can block starlight. And then my brain went to a very natural place from this, which is the fact that we now know that most stars have at least one planet. And the way we have found most of these planets is through what is known as the transit method. The idea of the alignment being such that those exoplanets pass between us and their star, blocking some of their star's light from us. So just as Venus can move across our view of the sun and block some of our sun's light, a distant planet can do this, and when it does, we can watch the brightness of that star dip slightly, since the planet blocks some of it. And of course, the size of the planet will affect just how much the star's light dims. And so by looking at factors of both how much it dims and how long that takes, and how sharply defined those edges are, you can get all sorts of information about the size of the planet and its orbit and its mass and all sorts of cool stuff. Here is a real data set of one of these transits, where you can see at the top there, the nominal starlight is at 1 for 100%, and then it very noticeably dips, but if you look at the scale here, I mean, overall, not much. It dips down to 97.5, and that's actually a very dramatic transit. Most of them are far, like they're in the 99 point something percentage. And the way that we found these was, for the most part, using a telescope called Kepler. We now have TESS, which is the updated one, but the way it does this is it doesn't look at one star. It stares at one part of space for days and just images a whole bunch of stars. And then basically computers and people pour through that data, just going one star at a time, looking for any signs that the starlight dimmed in the time period it was staring at that piece of sky. So that is the reason why you don't get these discoveries right away. The data gets taken, and then it can take years of people looking through these candidate stars as a computer looks for places that look suspicious, and then a person looks through and confirms them. So we have found over 5,000 exoplanets, and there's like another at least 5,000 candidates that are awaiting review of the data by a person but have been flagged by a computer. As I said, we now know that planets are the norm, and that when you go outside and look, most of the stars you see in the night sky probably have at least one planet around them. Now, the transit method does have a problem in that it is extremely biased. And so trying to answer the question we've been asking for a long time, other than just are there planets around other stars, but is the solar system typical or weird? How does it compare to other planetary systems? We actually don't yet have a really good answer to this, because of how biased this method is. So biased, of course, means that you're not going to find all cases equally, right? If I want to take a sample of people and I go to a preschool, I'm not going to get a representative sample of the entire population. I'm going to get a few adults and a lot of very young children. And that is biasing myself toward young ages. So the same thing happens with the transit method. First of all, we are biased toward the smaller stars. If the star is smaller, it's easier to block a larger percentage of its light with a planet of the same size. So the top two images there show you've got a same-sized planet, but with the smaller star, a greater percentage gets blocked, and therefore the transit is easier to spot. And so we will be biased toward those small stars. Now, this one is not so much of an issue because it turns out that small stars dominate our galaxy. Most stars in the galaxy are much smaller than the sun. Most of them are red dwarfs. So that one's actually not too much of an issue. But the other one down there is actually a much bigger problem, that we are biased toward larger planets, right? If the planet is bigger, then it's easier to see that dip than if the planet is smaller. So the first ones we found were huge, super Jupiters. They weren't Earth-sized planets. And we are starting to find those, but it is a lot harder. Now, the other thing that we are biased toward are planets close to their stars. Let's think about this. You're an alien. You're observing the sun. You'd have to stare for a year to be guaranteed that you saw the Earth transit, assuming the geometry lined up. We didn't stare that long. That's a long time to stare. And Earth is one of the closer ones. Here's a transit that's ticking along. Look at the axis, time in days. This planet, Kepler 4b, is ticking around its star every 3 Earth days. That's its year. 3 Earth days. That means it's super close to its star. It's what we call a hot Jupiter, which is basically taking something the size of Jupiter and putting it incredibly close to its star so that it's so hot that it has like metal in its atmosphere. I mean, it's insane. And also they tend to be tidally locked. which is the same as Earth's moon. One side always faces the star and one side always faces away. So you have one side that's just getting blasted with the star's light and the other side that's always experiencing nighttime, and people are modeling all the interesting weather that can happen as a result of that. But we are very biased toward these close planets because of the fact that we only stare for so long. So we're not very likely to catch these really long period planets like we see here in the solar system. Because even if you caught one dip, if you don't catch a second one, you have no confirmation of it. So even if you watched for a year and you saw the Earth blip, you wouldn't have a follow-up observation. And sometimes the data looks like this. Now what you're looking for, of course, is a nice regular ticking along like that first one I showed you. And yet this one looks pretty chaotic. Anyone want to venture an idea why the planet is not seeming to orbit at a consistent rate? Why this looks random? There you go. Yeah, if you tease it out, we've actually got the work of 7 planets going on here, all ticking along at their own rate, and so each of them producing a pattern. And if you look at that last one at the bottom, we only caught it once. So that is, again, that issue of, do we really know how long its period is because we don't have a second one? Yes? Oh, you asked another very good question. That is something that technically we should be able to see if the instrument is sensitive enough. We have had a few pieces of data that could be a moon. So there's been a few potential detections of exomoons. We have nothing that has yet been, yep, that was definitely a moon. We assume that considering that there are almost 300 moons in the solar system among 8 major planets and dozen or so dwarf planets and dozens of minor planets. So the fact that moons are prevalent here means we would expect moons to be prevalent elsewhere. So they're there, and it's just a matter of getting the instruments and analysis sensitive enough to see it. But yes, you should potentially be able to also kind of on the edges, an extra blip on either side of the transit. You could pick up an exomoon if it was big enough. So yes, but we haven't quite done something yet that we're definitely sure is that. So this is the famous TRAPPIST-1 system. 7 Earth-sized planets orbiting a single star very closely. So look up at the top one there, 1.5D. That's a day and a half. Every day and a half it goes around its star. And the periods increase from there all the way down to this last one, which again, with only one pass, we're estimating that it's anywhere from about 2 to 4 weeks for its year. So how in the world do a bunch of planets get nestled up that close to their star? Well, partially it's because they're not orbiting a sun-like star. They are orbiting a red dwarf. So what we're looking at here, the one thing that's not accurate is the sizes of the planets, all right? Those are just blown up so we can see them, but they are all rocky planets. This is actually their system in comparison to Jupiter's system with its 4 main moons. So those are shown to scale. So this is a planetary system that is closer in size to here in our solar system, a single planet moon system. Also, you can look here and see this is the size of their star accurately shown with respect to those orbit sizes, and this is how big the sun would be if you put it in this planetary system. So the sizes of the star and the sun with respect to the size of these orbits is also shown to scale. Yes? Exactly. So yeah, that's a weird thing of it. A technically becomes the star itself, and if there's more than one star, then you might not start planets until C. So it's basically designating them as part of the whole system. But yes, TRAPPIST-A is technically the star itself. Good point. So yeah, so this is a nestled, close little in tight system. For comparison, you would have to shrink those orbits down a scale of 25 times, and they would fit here within the orbits of the inner solar system. So compared to the solar system, this is a teeny tiny system. And you might say, well, like, couldn't there be other planets farther away? Yes, totally. There could be other planets farther away. But we just haven't stared at the star long enough to see them. Now, we have actually directly imaged some planets that are orbiting their stars very far away, far enough that we actually can resolve the difference between the planet and the sun. And in that case, we're biased toward planets that are very far away, because the farther away the two objects are in the sky, the easier it is to resolve them. But the transit method is definitely biased toward small stars and planets that are very close. For the sizes of the TRAPPIST system, everything on this chart is to scale. So you can see the size of Jupiter and its 4 largest moons compared to the size of the TRAPPIST-1 star and its 7 so far discovered planets, and the size of the sun down there in the corner with respect to the 4 inner rocky planets of the solar system. So the star is much smaller, but the planets are of similar size to planets of our inner system. And yeah, the star's not that much bigger than Jupiter. Weird quirk of things. Once you get to the size of Jupiter, if you keep adding more mass, you generally get more denser than you get larger. So the smallest stars are actually on the scale of the size of Jupiter. I think there's even a weird smallest star that's smaller than Jupiter. I don't even fully understand the physics of how you do that, but apparently you can. Now, what about the temperatures? Because again, they're really close to their star, but the star is much cooler than the sun. Red dwarfs are at a much lower temperature. So this is the effect of being kind of far away from a bonfire or nestling in close to a tiny little campfire. If you account for the difference in the temperature of the star and the amount of heat that they're pointing out, you get this plot. So on this is talking about the illumination. How much heat are they getting from their host star? On this scale, Mercury is getting this much heat from the sun, and TRAPPIST-1b is getting this much. So TRAPPIST-1b is getting actually less heat on it than Mercury. TRAPPIST-C and Venus are actually getting almost the exact same amount of heat from their stars, and TRAPPIST-D and Earth are getting almost exactly the same amount of heat from their stars. E is sort of between Earth and Mars, F is a little colder than Mars, and G and H are both even colder than that. But the key thing to recognize there is in the solar system, our Goldilocks zone, that habitable zone, runs from just about Venus to Mars. And in this case, there are definitely 2 planets solidly in that range in this system. So not only are they about the same size as planets like Earth, they're also receiving the same amount of heat from their star that Earth is, which means we would expect some similar surface temperatures on these planets. I love this little piece of artwork here, where the closest planets you're thinking about water is water on the surface, so the closer ones we see steam, nope, too hot for water. The middle ones we see some wetness going on, yes, liquid water could exist, and then the outer ones it's like, yeah, mostly icy and frosty. But this system holds an amazing potential for possibly having 1, if not 2 worlds that are extremely Earth-like. And back to the whole thing, remember we were talking about eclipses? The planets are so close together in this system that if you lived on one of them, you would be able to see the other planets in your sky, not as dots of light like we see our other planets, but as actual objects. And you would regularly be treated to transits, I guess, not eclipses, but yeah, you'd get a very pretty sky, in my opinion, on this planet. I forget which one this is supposed to be. This looks like one of the outer ones, looks a little cold. Yeah, so cool. We can find planets. We can figure out how big they are. We can figure out how big their orbits are. We can figure out maybe even about what temperature they are on. But what about whether or not there actually is water there? And for that answer, I want to go back to this picture. The idea that if your eclipse or transit is being caused by a body that has an atmosphere, some of the starlight passes through that atmosphere. And so not just the dimming of the star, but as this shows, you block it in the black, but then the blue here is the atmosphere, exaggerated, of this planet, and the star's light is passing through it. This is kind of the effect that you're looking at. For the most part, it's blocked starlight and regular starlight, but a tiny fraction, we already saw what a tiny fraction is that actually gets blocked. A tiny fraction of that is light that passes through that planet's atmosphere on its way to Earth. And when you pass light through gas, it changes its color. And it does that depending on what the gas is made of. So yes, you could potentially have the star's light passing through the atmosphere of the planet, and we can send it through a prism or a diffraction grating, spread it out into a spectrum, look for where the colors are missing, signifying where certain chemicals have either scattered or absorbed those specific colors. And so in this way, we actually can tease out what is in the atmospheres. So yes, we can answer the question whether or not there is water in addition to other things. And this is a big part of what JWST is allowing us to be able to do, is it has the kind of capability to do this. So we're basically looking for signs of life in there. So one thing you could look for is the sky blue? We know that the sky on Earth is blue. Pluto also gets a blue sky because of nitrogen. Is there oxygen? All right, Earth has no business having 20% of its atmosphere oxygen. At this distance from the sun, it should be too warm for that. The only reason we do is because of photosynthesis. And so if we saw one of those planets that should be getting the same amount of heat from its star as Earth with 20% oxygen in its atmosphere, that'd be pretty interesting, because that only happens on Earth because of life. And there's vegetation jump. There's that idea that you can see certain very dramatic features other than just that oxygen that happens when you have photosynthesizing things on the surface. Water vapor, we have found planets with water vapor in their atmospheres. We might be able to tell if there's volcanism on these planets or not by the chemicals that are in it. And yes, maybe even detect things like methane that are byproducts of things like bacteria as well as cows. And for the record, in defense of the cows don't fart, they burp. So let's be clear that the methane from cows is not cow farts, it's burps. And for some reason that's more socially acceptable at the dinner table. I don't know, but just so you know, it's not cow farts. So yeah, there's all sorts of potential here for ways to discover the surface conditions of these planets and possibly see signs of life. And there is where my little brain finally decided to take a rest and say, okay, I think I've covered that topic. So, any more questions about any of that exciting ride that we just went on? All right.
It's from Mike Blake asking, have we seen any binary stars with planets?
Ooh, so, okay, the fact is that yes, about half the stars in the galaxy are not single. They are binary or higher. In fact, our nearest neighbor, Alpha Centauri, is a triple star system. So Alpha Centauri A and B are two stars, one that's a little larger than the sun, one that's a little smaller than the sun, that orbit close to each other. And then Alpha Centauri C, also known as Proxima Centauri, is a third star that is a red dwarf, much smaller, that orbits much further out. And currently, with where that orbit is, that makes it the closest star, technically, to us other than the sun. I will clarify that. Yes, the closest star to Earth is the sun, I know. So that's why we call it Proxima Centauri, because it is officially the star that is closest. We do believe we see evidence for one, possibly two planets in that system. And that's just the next door neighbor. Though I think both planets orbit A and B together. So if you had two stars that were orbiting very close to each other, you could have a planet that orbited both of their center of mass, basically. Yes, you get Tatooine for Star Wars fans, yes. So we've actually found multiple planets that we would say are Tatooine planets that are orbiting a close stellar binary and would therefore always have 2 suns in their sky. Yes?
Star system, doing the same techniques that we do here and allowing for the same amount of time observing, and we looked at our sun here, how many planets do you think they would see that have discovered?
Current capabilities, I think they'd be hard-pressed to see any of our planets without an enormous amount of luck. Because, as I was saying, the bias is both toward planets with very short years or for very long years. And actually, there is a big gap in our ability to detect planets in the range that we have here in the solar system. So actually not great right now. We might totally miss that there are planets around the sun if we're using the same techniques. We're getting better at it, though. We can stare at patches of sky for longer amounts of time. We can resolve distances between stars and their planets better. So, but yeah, it's a quirk that the solar system is actually in a range of, right now, of a lack of data that we have, a lack of an ability to find planets. So, interestingly, no, they probably would not have found any of the planets. They might have found, like, maybe Neptune. Or maybe if there's they think there might be another large planet out there. Maybe they might have found that and we still haven't. So yeah, it's an interesting thing of no, they might not have found any of our planets yet if they're doing the same thing. But yeah, so you can have planets orbiting multiple stars. Also keep in mind those planets they're orbiting in Alpha Centauri. Proxima Centauri would be orbiting outside of those planets. So it would be like I don't even want to say a super bright star. It would also follow, it'd be kind of like, okay, imagine Jupiter were a small star in our sky. It was like another small sun in our sky. And that's what these planets would see of their other thing. Any Isaac Asimov fans in here? Anyone read the story Nightfall? It's one of his short stories, widely regarded as one of the best science fiction pieces of literature. It's short. There's even a YouTube video of someone reading it, so you don't even have to pay for the audiobook if you want to listen to it. I don't want to give away much about it, except that it deals with that exact issue of what if you're a planet in a system with more than one star? And what does that do to how you perceive things like day and night, and how you can observe the universe if you're in that system? And I'll tease it for there, but seriously, read it. In fact, read everything Isaac Asimov wrote, practically. Nightfall. Nightfall by Isaac Asimov. Apparently, the Chronicles of Riddick was somewhat loosely based on this idea as well, but I mean very loosely. But yes, seriously, check out Nightfall. It was actually, I don't remember if it was that one or The Last Question was the first thing I ever read from Asimov. They're both short stories, and they're both absolutely amazing. So I was hooked from the start because I got hit with like 2 of the best things he ever wrote. And now I have volumes 1 and 2 of his short stories, and I've read them all multiple times. And they're all written like in the 50s, which just is mind-blowing. I recommend all of them. Yeah?
I had heard at another talk that I attended, because the Earth and the Moon are getting closer together, as you said.
Farther.
Farther, I'm sorry.
Yeah.
Farther. That eventually there won't be any more total solar eclipses. They'll all
Right.
be annular.
Right. I think I was getting to that point and never got there, so thanks for bringing me back to
Essentially lose total solar eclipses. An actual thing that occurred to me when I was like driving here was that I really would want to know when. Okay, thank you, because I've been wondering, like, because astronomers say something like that, and you're like, well, is that in 100 years, in 1,000,000 years? What are you talking here? So, okay, in 400 years, they think we might not get total solar eclipses. So we're really like alive in a cool time right now where we can get both total and annular. A few of those paths are what we call hybrids, which means the moon is at such a perfect little average that the thing starts out total and then changes annular in the middle of it, or the other way around. So the moon right now is really like dancing with this like just slightly bigger or slightly smaller than the disk of the sun in the sky. I mean, we're also lucky enough now, we realize, to be around when Saturn has big, bright, beautiful rings, because apparently that hasn't always been the case and won't always be the case, though that's on a much longer time scale. I like the headline that's like, Saturn's rings are younger than flowers. Flowering plants evolved on Earth before, at a time where Saturn had no rings, apparently. So.
Planet that had several suns orbiting each other, you could watch the suns lined up.
If one of your suns passes in front of your other suns, is that an eclipse? I love giving talks for this reason. I hadn't even thought of that. Yes, you would sometimes, I guess, if you were aligned correctly, you could get that effect.
Would it be a little bit brighter, or would it be twice as bright?
So
Or
it would
would
be
it be
dimmer,
Oh, dimmer.
because
Star would block the light from the other star. There was a diagram I didn't really go much into, but if I pointed out here, there is a secondary, what they say, a secondary eclipse, which is a place where when the planet is over here, you're getting light from both the planet and the star, and when the planet passes behind its star, you also get a slight dimming because the light from the planet is being blocked from the star. So, yeah, during that kind of eclipse, it would get darker because, yeah, you'd be losing the light of one or more of the suns. But, wow. What a cool thought. All right, well, I see you even ran with it and went further than my brain did, so now I have to add slides because you just brought up some really cool points that I have to add. So the journey continues. Thank you very much.
All right. Thank you so much, Zoe. Fantastic presentation, as always. I do want to mention, on the topic of solar eclipses, of course, with the one next week, a week from today, Kopernik, we aren't just open for an observing session, but we do have a special live stream planned that day. I don't think Sasha is in here, but Sasha Zaleski, one of our educators and a member of the Kopernik Astronomical Society, will be visiting Texas that day. She'll be in, just outside of Dallas, I believe. And we've set up a dual stream. So she'll be capturing the eclipse event from Texas, and we'll be up here capturing our partial eclipse in New York. And we'll have both of those side by side. There's Sasha in the back of the room there. So
we might drive by each other.
Well, that's right. You mentioned you were going to
right,
Texas.
Yeah. I'm landing in Dallas the night before, and then I'm going to leave in the morning and drive to Odessa. So yeah. So look forward to that stream next week. Awesome.
And now it's break time, dinner break. So I don't know if you had anything you want to mention, Art? No. Oh, you're all okay. I wasn't sure.
Thank you very much. Yeah, I didn't know.
All right. All right. Well, we're all set. So we'll be back at 7 p.m. for the next presentation.
I did bring it. So yeah, if we want to go, let me pack this up, and then I can bring it in. Okay.
had to breathe a sigh of relief when the Congress voted not to shut down. So we got these. So make sure you take home some of these beautiful maps of the moon. And on the back, lots of information about the moon. Why do we have to get to know it? Well, what do you think? Oh, wait a second. I know I'm surrounded by astronomers who hate the moon and don't want to see it come up, and so that's why they recognize that this is the night of the new moon, right? Pretty much. So the moon isn't coming up until about 1 o'clock, I think it was, Katie time. So I don't think anybody's going to be observing the moon tonight. But Jeremy, when you see that, there he is. Thank you. When Jeremy gets a chance to talk about it in about 2 weeks, right? Hello, is that working? Okay, when Jeremy is doing his moon, it'll be a way better moon to observe in a couple weeks. Okay, we're going to get started, and I'm going to end with some wonderful news about who's going, and I can't wait to show you, but let's get started, okay? What do you think we turn the lights partly off? Do you have a map? Do you have a map? The front page is the most important, but the rest are extra information. Can you see it? All right, can you see? Do we need more lights or less lights? Are you okay? You're looking up there, okay. All right, well, I mentioned Latin. It's very important, but an Italian priest / astronomer. I guess that's kind of a funny job, but named Giambattista Riccoli decided the names for the mare. And it's really just dark spots that are nice and smooth and flat on the moon, and he thought that they must be seas or oceans or something like that. So you can see the names and their translation. So that was decided way back in 1651. But I'm not into history myself. I'm more into future tonight, so let's get started. The way I figured it, the moon's coming out at 1 o'clock. Let's see. There's a tiny little rock in here. I'm going to pass that around. Take a look at it and pass it to the next people. Got another one here. Thanks a whole lot for all the people who helped me set up, because I've got 2 bad knees and the doctor says I have to have them lopped off. Especially Art. Hey Art, thanks a bunch. One of the things he fetched for me was this rock. This beautiful black rock is called basalt, and it's one of the main ingredients of the surface of the moon. Now, what's so important about the rocks? Why do we have to pick up the rocks and bring them home and study them? What do you think? Any ideas? No? Well, let me just tell you that we're spending millions, billions actually, to go to the moon to get ready for a pit stop on the way to Mars. We decided that Mars was a target we could do in the next decade. So fingers crossed we can do that. But first, why can we stop at the moon? What good is that? Well, this rock, if you've already seen it, good, nice and dark black, it's loaded with oxygen, titanium, platinum, and other minerals. And you can use it for building rockets, making rocket fuel. Thank you. Did everybody catch it? All right. There's a lot of water. We're going to show you that on the moon. It's just mostly what? Frozen. Yeah, but I think we can use it. So what's water? H2O, right? So a lot of the craters have H2O frozen at the bottom. especially the one that we're aiming for. Now, if you've got the card that says the south pole of the moon, I'm going to show you some cool, really cool pictures of that. But on the back, do you see those blue dots? Those are places where there is definitely some frozen water, okay? So take a look at the back of those lithographs because they tell you a lot, okay? Now, if I didn't have a basalt in my hand, I would say check out the rock. Would it be igneous, metamorphic, or sedimentary? What do you think? Basalt. What's your guess? Igneous is the kind that gets melted down from lava. Sedimentary is associated with water. And metamorphic is a rock that's gone through pressure and heat. What do you think? Igneous is the number one, yes, what we think. So the igneous rocks on the surface of the moon are similar to that rocks. Those are not moon rocks, actually. But I know Drew's going to get us a moon rock up here one day. It'll be awesome when we do. And it'll look a lot like that little black rock because most of it is basalt. So can you crush it up and get oxygen out? Well, that's the story. I think it's loaded. The regolith is loaded with oxygen. All right, so the rocks tell us a lot. The water tells us a lot. We want to go there for those two reasons, and partly because we're just really curious. We need a place where we can pit stop on the way to Mars. Let's take a look. There. Before we move on, which one is the one where Apollo 11 landed? Anyone? Yay! Okay, Sea of Tranquility. By the way, I remember this one because it's almost perfectly round. And if you've been exploring the moon a lot, you know all these by heart. Okay. And this is the beautiful Clair de Lune that I showed you earlier, so I'm going to come back to that later. So a little bit of fiction here. Somebody has been trying to make it look real for a long, long time. Which one's the oldest movie? 2001, Ad Astra, or Apollo 13? Which one's the oldest? 2001, don't go by the title. Okay, 2001 was made in 1968, before there was anybody on the moon, and that's amazing, you know, that it really is so cool. Although they did kind of exaggerate a little bit. I've seen Ad Astra. It was pretty realistic, and Apollo 13, I know it had a really good hand in it. Jim Lovell helped with that movie, yeah. Okay. So International Observe the Moon Night is the actual name of this, but it's not going to happen tonight. We're going to observe the moon in about 2 weeks. It's Friday the 20th, right? Friday the 20th, come back and you'll have Jeremy's version of International Observe the Moon Night. But it's all over the world. People, millions of people all over the world are waiting for the sun to go down so they can see the moon. This particular night isn't so good. All right. Our friends at Goddard Space Flight Center asked me to ask you, do you have any thoughts? What comes to your mind when I say, what is your favorite memory of the moon? I'm going to tell you just one, real quick one. One of the many things I've done in my 50 years of teaching is take telescopes out to the people. And there was a group down in Pennsylvania, and they were little tiny kids. Some of them were age 4 and up. Maybe somebody like that here. Yeah, okay. And they looked in the telescope and saw the moon. And one little boy looked down and went, of course, wow. I have to get a wow, right? But then he looked up at me and said, how did you get the moon in there? I just had such a great time with that. I hope you understand. All right. Are you thinking something great about the moon? Or are you thinking that the moon gets in the way of my Trifid Nebula? Okay. Good thoughts, I hope. Okay. Moving on to the next video clip. Now I'm going to kind of push a little bit more on the names. Let's watch. This is what we call a moon phase libration. And the same people that made the Clair de Lune put all the LRO videos together to make this. This is a full year of the moon. Now I wanted to show you just one really important part. Following the date here, we're up to February. We started in January. Now this is really neat. This is how far away the moon is. And these are diameters of the Earth. So if it's 32, it's 32 Earths away. If it's 28, it's the closest it ever gets. Now, when it gets super close, people call it a supermoon. Yeah, right. Okay. Does it happen often? Yeah, it happens quite often. But here's the thing. It's not full and close all the time. So let's watch. Here it is. Well, it's almost 28, but it's dark, okay? Why is it dark? Looking at the position of the Earth and the moon as it goes around us, and it's going laps around the Earth the same time as it does for the Earth. Same direction to the east. Okay, so now we're in June. Oh gosh, that was a good one right there. Got a full moon and it's close to 28. Let's see what happens in July. Here it goes. Move it, move it, move it. Okay, that's pretty good. That was probably a super moon we had in June and July. What do you think? Yeah, I think so. Okay, usually in the summertime, I don't know why. Maybe somebody can answer that. Okay, so this is an interesting symbol here. You can download these every year at nasa.gov. NASA.gov, very simple. And then go to the search, and it's called a libration map. I think you're gonna love it. By the way, we get a full moon this year for Thanksgiving and for Christmas. Gonna be fun, yeah. All right, let's move on. You should have a map like this. For the first time, the LRO has finally gotten every square inch of the moon photographed. The old maps of the moon that Kopernik has, like up on the book rack, they don't show the bottom with the South Pole. So you want to make sure you get a newer one, about less than 10 years old would be good. Okay, so study that. You'll be able to tell. Of course, there's an amazing difference between the side facing us and the side facing away from us. But there are little robots running around over here on this other side. I don't know of any humans that are over here. What happened to my laser? There were a couple of robots over here. I don't know that much about the far side. I think there's a lot to learn, but it's also a lot more dangerous, so I would stick to this side. And down here at the South Pole, you're going to see what that's like in just a moment. Here's the tricolor version of the topography, and you should have a map of that if you have one. Notice the colors, like red are the highest level, and the blue are the lowest. The Sea of Crises, right? Okay, awesome. I think that this is a beautiful thing, to be able to see every inch of the moon. This is made by the LOLA, the Lunar Orbiter Laser Altimeter. And a student sent this in to NASA, and they would like me to show it to you because she lives in Brazil, and during the sickness, the COVID thing, she took this picture, and she accidentally got another object in the picture. Can you find it? Woo! What is that? It's Saturn, yeah. Wow, that's pretty cool. So that's what it looks like in Brazil. Everything kind of upside down a little bit, depending on which way you're looking. Now here's some new data that just came out. The full map, excuse me, I'm going to accidentally lean on this, of the temperatures. And what color is the coldest? Oh, the purple. It's close to 400 below 0 Fahrenheit. We think it's the coldest place in the solar system, even more cold than Pluto. And I thought I'd pop this little image in here because it reminds us about the altitude. Here's the elevation guide over here. And notice that Shackleton Crater looks like a teacup. It's got purple at the bottom, and that's where the frozen stuff is. So that's what I tell the kids. That's where you put your frozen pizza and your cheeseburgers when you're not going to eat them yet, because they're going to stay frozen for a long time. And so we think the water in that particular crater has been there for frozen for 3.5 billion years. What does old water taste like? Well, I think the water that we drink here on Earth is old. Yeah, we called it dinosaur pee or several other things. Do you understand what I'm saying? The water we're drinking is the same water that's been on this planet for a long time. It's just reused. Okay, so we want to take a look at this very special water on the moon. Some other new data. This is a fresh crater that was exploded recently. I didn't get the date on that, but she told me this last week. So Andrea Jones, thank you, down at Goddard Space Flight Center gave me this image. You can see the ejecta flying out. Very dangerous place. So I'm going to bring it up later, but think about how you would be safe on the moon if you're going to live there from impacts like that. Okay, we would like you to check this out. This is some other new data. The incredible shrinking moon. The top picture and the bottom picture. The bottom one was originally, several years ago, And then the top one is recently, we lost a half a kilometer of the moon. Let's see. More than about 150 feet skinnier over the last several 100 million years. Wow. So what happens when the moon shrinks and shrinks and shrinks, even if it's only a few feet? Do you think the density would change? Would it change its position in space? Well, we do know that the moon is moving away from us about 3 centimeters a year, about the length of your knuckle. 3 centimeters. How will the size of the moon change and the mass and the density with the shrinking? These lines represent moonquakes. And one is folding over the other. Does that make sense to you? Looks like it, sure. More new evidence. Let's take a look at the Apollo area.
Listen, Tranquility Base here. The Eagle has landed.
Okay, you're seeing a blue dot where Apollo 11 landed. On the 45th anniversary, we took some of these pictures with the Lunar Reconnaissance Orbiter. That's the lunar module. You can see the people's tracks, Buzz and Neil's tracks to the other crater. And then they have a program that allows it to be turned 3D. I think a lot of us have seen this information before. It's been out for a couple of years. Thanks to our friends at the Goddard Space Flight Center. Oh, let's go to the next one. Okay, now let's see the South Pole.
Artemis is our 21st century return to the moon. Together, NASA, international space agencies, and a growing global space industry will explore Earth's nearest neighbor with advanced robotics and our next generation of astronauts. But where will our astronauts explore? The moon is a treasure trove of scientific discovery, and NASA has its sights set on the South Pole. This mysterious region features soaring mountains and deep craters, leading to unique locations that experience nearly continuous sunlight, in contrast to nearby depressions that never see the sun. Artemis III will mark humanity's return to the lunar surface for the first time since 1972. NASA has identified 13 regions near the South Pole that meet safety requirements for landing and present opportunities to search for lunar resources. Each region can also help us learn more about the history of the moon and gain a better understanding of our place in the solar system. These 13 candidate landing regions represent a diversity of features in the lunar South Pole, ranging from the summits of mountains rising miles above their surroundings to the rims of large craters. These features together act to both expose and preserve billions of years of geologic history. Using robotic orbiters and rovers, NASA and the global science community will continue to study these regions before selecting the Artemis III landing site. The astronauts selected for this bold expedition will literally and figuratively shine a light on some of the deepest, darkest areas of the solar system, revealing ancient secrets of the universe.
NASA.gov, you can get that same video. Also on YouTube. Okay, let's go ahead. So, who's going out there?
I'm Ernie Wright. I work in the Scientific Visualization
Wait a minute,
Studio
I
at
wanna pause
NASA's
that.
Goddard Space Flight Center.
I have to pause it because it's not the slide I was expecting, sorry. But this one I added at the last minute and I just recall. This is going to show what we think it would be like if you're standing on that South Pole landing spot trying to find the Earth and the Sun. Let's take a look. This is a simulation, yeah. No, I didn't want to do that, did I? Okay. Back. Try that again. There we go.
I'm Ernie Wright. I work in the Scientific Visualization Studio at NASA's Goddard Space Flight Center. We're looking at a computer model of the view at the South Pole of the Moon. This is like a time lapse to show the motion of the Sun and the Earth and how the shadows change over time. Things don't rise and set in the usual way here. The Sun travels around the horizon, never getting more than 1.5 degrees
It's like you're
above
upside
below
down.
it, so there are always these long shadows. And from here, the Earth appears to be upside down and rotating backwards, but that's just because of our point of view. The Earth doesn't move much in the moon's sky. It's always in roughly the same place, just sort of bobbing around. That's true everywhere on the near side of the moon. It's a consequence of the moon always pointing the same face toward Earth. It takes about a month for the Sun to make a complete circuit around the horizon, and every so often, it'll pass behind the Earth, creating an eclipse. I've slowed down time here a little so that it's easier to see. On Earth, that would be a total lunar eclipse, the moon passing through the shadow cast by the Earth. But if you're standing on the moon, it's an eclipse of the Sun. The terrain at the South Pole is especially rugged. The rim of Shackleton craters in the foreground here, and the mountain off on the horizon, unofficially known as Mons Malapert. It's about 85 miles away. Shackleton crater is about 13 miles wide. Not quite as wide as the Grand Canyon, but it's twice as deep. Sunlight never reaches the crater floor, so temperatures there are around 300 degrees below 0 Fahrenheit. This model of the terrain is made possible by Lunar Reconnaissance Orbiter, which has been mapping the surface of the moon from lunar orbit since 2009. LRO's maps will be incredibly important for exploring the moon and locating water and other resources there.
Perpetual sunshine. That's what we are expecting if we live on Shackleton's rim. Although we have put up with a lot of other things, it's a wonderful place to get energy. Do you recognize Ernest Shackleton's name on there? South Pole Explorer? Sure. Okay, so other explorers I want you to know before I go, we have some very brave astronauts getting ready to go to the moon. It's called the Artemis mission, and we just expect to go boing and boing, but it's not quite like that. So how far away is Mars? Depending on the time of the year, sometimes it's 150 million miles away, sometimes it's only 40 million miles away. So which way do you choose? The short one, right? Yeah, okay, so you just have to wait for it to come over here. So we found out that we can't just go to the moon and live there. Landing on there is going to be a trick. So there's a huge battle going on with all these corporations competing for NASA's dollar and our dollar. Americans are paying for this. So you've seen the landings from SpaceX. They're very exciting. But will it work on the moon where it's lumpy and crooked a little bit?
Well, we have to prove it, and we have to see. Or they have the other kind of lander with the 4 feet that's very short that we just saw that they used earlier for the Apollos. There are going to be several corporations competing. I mean, they're already busy at work, and we need them now because Artemis II is ready to go. These are our brave crew for Artemis II. The plan is over here. They're going to launch from Kennedy, go around the Earth a couple of times, and make a nice halo-type orbit around the moon, and just do several revolutions around the moon, and make sure that everything works. They're going to test a lot of equipment, and they're going to see if that landing area is going to pass the test. So they are going to drop something, but I don't know what it is. We're going to find out, but these 4 are not going to land on the moon yet, okay? It will take several weeks, though. I can't wait to see what that turns out to be. And my friend, Dr. Gaidash, found this picture in his archives from many moons ago. You can see one of the astronauts in the picture. This is Jeanette Epps right here. She's our girl from Syracuse who's ready to go. And she's going to start off by going to the space station with SpaceX Crew 8. Crew 7 is getting ready to go now, and she's probably going to go up next year. She's been trying so hard to get accepted into the astronaut corps, and back and forth so many times. She hasn't gone yet. This is her first flight. But she was telling us that the one thing she was trained for that I thought was really cool was living in a cave in absolute darkness with the only light they were allowed to have were glow sticks for a couple of weeks. And that was to prepare them for possibly living underground. Do you think that's a good idea if you're going to be on the moon where there are impacts all the time? Yeah, probably. Somebody should probably live underground. We'll see what it looks like and if it's that kind of area that is good for digging up. So thanks a lot, Jeanette, for stopping by Kopernik. She was in our lab that day showing her how we did the Lego animations. We still do that, don't we? Yeah? Okay. Legos? Sure. Okay. So, up in the corner, do you see that little girl? Right there? She's representing the first woman, and NASA promised the first woman would probably be a lady of color, if we can, if it works out. And there's a wonderful little book that you can get by just typing in first woman in your Google, and you'll go to the website and it will actually read you the story, and it's just like reading a comic book, a story about a girl who grows up to be a scientist and go to the moon. All right, so check that out. Artemis 3, that says phase 1, which means they're going to be landing. Artemis 3 is up for grabs right now. We don't know who's going to win the contest, so let's keep our eyes open. Go to YouTube and launches and keep track of who's getting launched and what they're going to try. And they have to land safely many, many times. So overall, it's got to be sustainable. We have to be able to live there on our own. So if you bring enough food, you have to get the water from the bottom of the crater. Maybe you could survive there. It is American-led, yep. A meaningful, long-duration human mission. It's got to be the kind of thing you could stay for weeks and then come back home. But what I love about the moon, too, is that you could make it home in 3 days if you have to. Space station takes 3 hours to get home, and the moon takes 3 days to get home if you're hurt or you can't make it. Let's enjoy a little video clip from NASA. If I can find it. There it is. This is one of my favorites.
Beyond the atmosphere.
astronauts
Yeah.
to people who did the activities. It was really cool. You know, did anybody see Zoe's planet that she had up here? That no magic planet. They had several of those magic planets, and one of our jobs was to teach people the planets. It was really fun. It was exhausting because it was like thousands of people, and they all wanted an astronaut. It was so cool. All right, so thank you all for making the trip, and can we have the lights on?
Yep.
And anyone who has a question, I'll try my best to answer. And if you did not try out this is a gift to Kopernik from NASA. This is the Braille version of the eclipse coming up this Saturday, a week from today. Write this down. 12:04 to 2:30. We're having a solar eclipse, but it's only going to do about 1/3 of the sun is going to get covered up here in Binghamton. Doesn't thrill me too much, but you have to be careful because if you don't use the glasses or other methods, you could hurt your eyes, okay? But they tell me that even if it's cloudy, next Saturday, 12 o'clock to 2:30, right? It's going to get a little bit dark, not very dark, but you will notice the difference. So if you're outside and suddenly the birds stop moving and they're not tweeting anymore and something else is weird, I wouldn't doubt it. But then the other eclipse, which is way more exciting, right? Dr. Gaidash is even leaving town so he can see that. Right here in New York, we're going to be almost in the middle of that eclipse. And what I mean is, I would say Buffalo, Niagara Falls, and Rochester are going to be totally dark that day. April 8th. Write it down. April 8th. At 2 o'clock in the afternoon will be about the height. I've been studying the eclipses as well, and my brain is a little screwed up. But I know that it's April 8th, about 2 o'clock in the afternoon. It is going to get dark. Whether it's raining or snowing or anything, it's going to get dark. So I'm even thinking this teachers and the kids in the schools, it's a Monday. April 8th is a Monday. So
We're going to be, 99% covered here?
Yeah.
Yep.
It's going to be really
But
dark.
that 1% will kill me.
Even if you're not
Yeah.
in Buffalo,
Yeah.
over here we're just on the edge.
But
So
the 1% of sun is enough to get rid of the thing
What?
around it.
Corona.
The corona, yeah.
we won't be able to see it. No.
You gotta be
I
told.
think Syracuse is just inside the edge, so.
They're really
Yeah,
close.
so you may be able, from Syracuse, you'd see
Real close.
the total eclipse
Yeah.
for a very short period of time.
Yeah, so I can tell you've been studying it too, and people have already booked their rooms in Rochester and Buffalo. So, but you could go farther up north, keep following that path, and there are lots of maps. Just Google April 8th eclipse. So it's a solar eclipse, not a lunar, okay? And it's going to be very exciting. The last time we had one here, Drew talked about it yesterday. 2017, were you here for that? 2017 when we had a 75% eclipse. We had 1,500 people here at Kopernik. We had, we've got 3 dinky little bathrooms and we ran out of water and soda and there was nothing, We had, how many glasses? I think we had 1,000 pairs of glasses we handed out. Yeah. So, by the way, your NASA money that you're doing with your taxes.
Do you have glasses for this one coming up?
I have Tish, poor Tish. I'm representing NASA. That means I'm not here. I'm going to be somewhere else. I'm going to be at the Binghamton Public Library. They asked for me first, so what can I say? I'm going to hand out free ones. I've got 250 And I promise they're not going to charge you for them if they're from NASA. They have to be free. But don't expect to get lots of them because they're really rare. A family named Moore, M-O-O-R-E, donated 5 million pairs of glasses for the eclipse. But that's the whole country, so every library who asks for them will get at least 100. So if you live near a library, you just say, do you guys have any glasses over there? And they have to give them to you if they have them. Okay? But don't ask for more than one, okay? Anything else about the eclipse or the moon?
I have a basic question about the moon. What is the difference in the material from the dark spots to the not dark spots?
Yeah, it seems to be freshly cooled lava in the mare, and they're nice and smooth. And they haven't been pummeled, so they're kind of new. You can tell if they've been hit a lot. There was this thing called the Great Bombardment about 3 billion years ago. That's what the rocks tell us anyway. And the mare are the smooth places that kind of leaked out when it got smacked into so much. And so if you pour lava over any big pile of rocks, they're going to melt, right? So if the lava came out and spread out like a big sea and then dried up that way. That's what we think. Yeah. But it's a good place to land. As far as we know, it's solid. Yeah, I don't know how many places are dangerous to land. So you saw the landing spots in the South Pole. So the South Pole has the water and it has the electricity we can get. And so, you know those guys that are making those really cool new batteries? Titanium batteries, right? Both Endicott and up in Syracuse, they're starting everywhere. We're going to need all of those because you're going to need to change the solar into electric and store it, right?
Where would be the best place on the moon to do scientific research?
Well, what do you want to know?
Well, this in general, I mean.
Want to check out the water? Go to the South Pole.
Okay.
Yeah.
Well, the backside will get you out of the noise from the Earth to some degree. Because it's
right. Okay.
Radio noise.
Radio
and stuff
noise.
like that. Yeah.
If you want to get away from the radio, you know the James Webb is on the other side of the moon, 1 million miles from here, and it's like being shielded by the Earth. The moon is shielding the Earth's radiation of all kinds. I guess we're transmitting stuff like TV, which could make it difficult if you're trying to talk and do emails and stuff.
Yeah.
Yeah, you're gonna have to set up your own station so you can talk to your friends and family. Yeah. Those are good questions, and I'm good. So I thank you all, and don't forget to take some of these back with you and study the back of it, because your grandchildren and my grandchildren are going to be going to the moon and then Mars. It's going to happen. Thanks a lot, Art. Thank you. For inviting me. That was fun. I appreciate it.
All right, thank you so much, Tish. And we're going to go on a brief break until a welcome to AstroFest 2023 for the evening before our keynote address, which that'll be welcome to AstroFest at 8 p.m. 8:15 is the keynote.
I can use some more.
That is from Pranvera Sinch. And she's going to give a talk on public education and outreach. This is what I'm particularly excited for. She established the astronomy outreach of Kosovo, and it really is a ground-up approach to astronomy outreach. So I'm really excited for that one, and that'll be at 8:15. So
great. I'm sorry. Thanks for
you.